Welcome, aviation enthusiasts and curious minds, to a journey through the skies like never before. We're about to embark on a thrilling exploration of the most unusual and innovative planes that defy the conventional norms of aviation.
It is a historical discovery worth its weight in gold. A truly important document of German aviation history is uncovered. It is not found in the archives or by any secret military personnel after the war. It happens instead by accident. On an ordinary day for this factory worker, he discovers a sealed canister containing a drawing. It appears to be a blueprint for the design of an aircraft. On closer inspection, the document dates back to the mid-1920s. What it turns out to be are the workings of a deadly state-of-the-art bomber, illegal in Germany at that time. Its origins are inspired by this strangely designed plane. It may look backwards, but the logic behind the design is truly forward in thinking. It is one of the original tail-first, canard-designed planes, and the concept behind it demonstrates Germany's desire to be at aviation's vanguard.
In the Ente, again the duck, late 20s, they had this design. Tail first, not really an airliner, but a few seats. The tail first design would allow you to triumph against the stall. The stall was very much a feared thing. You lose control, you crash. A canard, a tail first design, can say that if forward tail stalls, nose goes down, pick up speed, airplane stays in the air, all is well. The prototype flew around 1927-28, worked quite well.
It is an unconventional design by an unconventional designer. Heinrich Fokker is hoping to remove one of the pilot's biggest concerns since the birth of aviation, the dreaded stall factor. Thus, the design is catching the attention of aviation enthusiasts from around the world. Innovative as the F-19 may be, it is not without its flaws.
Eventually, it crashed. If you lose control of it at low level, it's deadly. And Mr. Wolf, the Wolf of the Focke-Wulf, he's the one who died in the crash.
With the death of their founder, and with military aircraft strictly forbidden in Germany, those at Focke-Wulf are now at a fork in the road. Do they keep on developing canard technology for peaceful and, most importantly, legal purposes? Or do they risk both the company's future and their freedom by turning it into a deadly weapon of force? In an extremely risky decision in the history of the company, the plan for the F-19 dramatically changes. Instead of being the originally planned sports plane, it is now going to be a deadly bomber, capable of causing tremendous havoc over Europe's skies. The man behind this madness is one of Germany's true engineering geniuses, Kurt Tank, who joins Focke-Wulf as a result of a company takeover. Being there every step of the way, he harnesses and perfects this technology into what becomes known as the Model 42. The source of funding for this ambitious project in an economically starved country is still unknown. However, there is one thing for certain. Germany's quest to rule the skies is something neither military defeat nor monetary limitation can stop.
Tail-first design was developed for a number of reasons. If you have a canard configuration, you have a very thin nose because your engine is behind the pilot. You can technically, at least in theory, increase speed with the same amount of power, which is good for combat aircraft. Also, because you have a fairly thin nose, you can improve, to a certain extent, pilot visibility.
When completed, this aircraft, powered by BMW's V12 engines and possessing a maximum speed of 200 miles an hour, is for Germany both her sword and shield. Any potential enemy will think twice about pushing around a Germany possessing an arsenal of aircraft carrying 20 200-pound bombs on board. More importantly, if Germany desires to reclaim her lost territories following the Treaty of Versailles, the Model 42 can put immense fear into both Europe's citizens and industries with its capability of causing enormous destruction. As testing rapidly advances, ironically, the rug is pulled from underneath them by neither pacifists nor neighboring European powers, but by the most militaristic regime in history. As Hitler's Nazi Party comes to power in 1933, the newly installed Chancellor's main interests are in maintaining and consolidating his power. An illegal aircraft project, if discovered, could be the end to his fragile rule. As a result, the project dies alongside German democracy. Although the Model 42's future is ended with the single stroke of a pen, the concept of canard technology lives on. Focke-Wulf obeys the government's decision, but at the same time rapidly develops what is known as short takeoff and landing technology. One of its crown jewels is the FW-61, the world's first fully controllable helicopter. Its creator, Professor Heinrich Focke's, much like his German predecessors, symbolizes that an idea can never be defeated, no matter what obstacles it may face. Had this bomber plane been approved for production on a massive scale, one can only imagine what impact it would have had on the Second World War. It is one of the conflict's greatest what-ifs. In fighting both Britain and the Soviet Union, it might well have tipped the scale in favor of Germany. The Model 42 thus may have resulted in a soaring victory and changed dramatically the outcome of the war in Europe.
I name you hero and wish you good luck and Godspeed to all who fly in this type. Yeah? Thank you very much.
Despite the enthusiasm at Handley Page, the mood in England at this time is anything but cheerful. By 1937, the drums of war are beginning to be heard across the nation. Never has this been more evident than at these factories, where the Harrow is being introduced in an attempt to showcase Britain's military power. Unfortunately, it is technologically years behind the now cancelled Model 42. With $400 million being spent on aviation in a single year, the government assures its citizens that they have nothing to fear with this powerful weapon on their side. However, the question remains as to whether these bombers can stand up to the growing German threat. These fears are finally realized as Britain's cities are repeatedly bombed by the Luftwaffe, causing enormous destruction and loss of life. The Blitz has now focused the world's attention to what the bomber is capable of doing. The nation everyone is looking to is in dire need of a solution to this deadly problem. It may be one of Britain's most unusual designs for a plane. At Miles Aircraft, this prototype, known as the Libellula, marks not only the resurrection of the canard design, but also exemplifies a company truly thinking outside the box.
People were very appreciative of the fact that Miles had this wonderful innovatory streak in them, and that they might come up trumps with something.
During the war in Reading, Berkshire, the factories of Miles Aircraft are working overtime, making a substantial contribution to the nation's war effort. What is capturing the imagination of the company's top designers is the reconstruction of a revolutionary aircraft. A plane that will capture massive attention with a design so futuristic that it is years ahead of its time. Hard at work with their initial sketches by ambitious and intelligent designers, the canard plane is reborn. In this factory, British men and women are side by side, hard at work putting together this complicated design. While their soldiers are fighting on the front lines, these workers have stayed behind. Their job is to maintain the production of wartime equipment on the home front. And a mighty task for them is to construct this unusual plane possessing a tandem wing arrangement, requiring countless hours of labor. Unlike standard aircraft, the Libellula M35 has its wings at different heights and at different lengths. The reason for this is that the lesser wing acts as a forward-mounted stabilizer, thus improving control, especially in regards to landing. With its shorter wingspan and not requiring them to fold, when completed the M35 is to be used as a carrier-borne naval fighter. Its sister plane, the second of the Libellulas, with an additional engine, is intended strictly for bombing purposes. Its creator, George Miles, says that when completed, the plane will resemble a dragonfly. In just 90 days, the first plane is built, remarkable for its time. Those at Miles Aircraft are determined to see what this plane can do once it is up in the air. Getting the plane ready for flight, engineers are putting the Libellula in position. As the final inspections are being conducted both underneath the plane and in the cockpit, the company, having a huge investment in the aircraft's success, hopes to put it into mass production shortly, pending government approval. Possessing a tricycle landing gear, the intent is to achieve complete stability when landing. At the rear of the wings are the corresponding vertical and horizontal stabilizers and rudders. Once in the air, the plane is able to fly at 160 miles an hour and climb at a rate of 1,100 feet a minute. Its canard features lend the aircraft well to both high and low-speed flight. With all of its advantages, however, the Libellula is not without its drawbacks.
So the Libellula, the problem was to control the aircraft for takeoff and landing. It had 2 sets of flaps with 5 settings for each set. So you had a potential 10 combinations. This was difficult because getting the right combination was one thing, because every time you changed the combination, it had some effect on the controllability of the aircraft. And it was really impractical.
Complexity becomes its Achilles heel. And despite the optimism from those involved in both the flying and the making of the plane, the military situation at the time dictates that the Libellula must come in for a political landing. In many ways, it is surprising that both versions of the design never go into mass production. However, its fate, similar to that of the Model 42, rests not on the aspiration of its designers, but on external circumstances. Britain, now with the United States and the Soviet Union as allies, is turning the tide against the German war machine. As a result, the demand for the Libellula evaporates. With prospects for the canard design now looking all but dead, miraculously, it once again is resurrected. This time, however, it is not done by any European power. Instead, it is done across the Atlantic Ocean, in America, the birthplace of aviation. Here, the canard design is reincarnated. The United States, referred to by Japanese Admiral Yamamoto as the sleeping giant, has awakened. Having an industrial capacity second to none, geography is the country's greatest asset. A massive labor force working uninterrupted, without fear of factories being bombed, is Uncle Sam's greatest advantage. And aircraft production is no exception. In terms of quantity, the United States is the undisputed champion. No European nation can even come close to their rate of production. However, while the country leads in quantity, it is quality that one aircraft company aspires to excel at.
But there was definitely a potential there. So Lockheed started to look at what kind of airplane could be designed around a turbine engine for high-performance aircraft.
It is Lockheed who believes it has the jet-powered solution for the fighter. One of its most secret projects of the war is the L-133 prototype, which is tested to see if this new technology can be harnessed into something tangible for the United States military. Thus, the canard design, an important component of the project, rises from the ashes. At first, the Army Air Force show interest in the project. The emerging military-industrial complex, however, dictates the final decision, with it becoming a case of quality versus quantity that ultimately determines the project's future.
They looked at it and sort of, well, this is all very interesting, but you have an engine that's a wee bit on the complicated side, and you're producing Hudsons for the Brits, Lightnings for us, you're producing light transport aircraft, and in some cases, like Lightning, for example, your deliveries are good, but may not be quite as good as we would like them to be, and you want to get involved in the design of a new type of engine and a new type of aircraft. Please slow down. Our enthusiasm is not necessarily there.
With war raging on in both Europe and the Pacific, a policy of producing what is known and reliable is enacted. Every second must be accounted for. With the possibility of the model not functioning properly, precious time must not be spent testing the unknown. Thus, the L-133 becomes, much like the Model 42 and the Libellula, an aircraft whose potential remained unfulfilled. There is no doubting, however, with its state-of-the-art technology, the development of the L-133 would have brought canard technology to a new level. It is the right place, just not the right time for Lockheed. To the employees at Curtiss-Wright and canard enthusiasts, deliverance has arrived with the XP-55, known as the Ascender. With the main wings located at the tail end of the fuselage, it is certain to attract attention due to its unique design.
Presenting the Army's new Ascender plane. With its elevator controls in the nose and its motor and propeller in the rear, this push-propelled fighter reverses conventional airplane design. Developed experimentally as the XP-55, the new plane gives forward vision for the pilot and a clear path for his gunfire. In action, the darting tail-first Ascender seems to fly backwards.
Its origins lie in an Army Air Corps flirtation with unconventional aircraft design. And nothing defines the unconventional like the tail-first plane. Despite a policy of turning out proven aircraft on a massive scale, there is some room for experimenting. Originally intended as a design to be powered by Pratt & Whitney liquid-cooled H engines, it is perhaps the best chance canard technology has of becoming more than just a blueprint or a workable prototype. Mass-scale production is the ultimate goal of its enthusiasts. After extensive testing, it appears that the Ascender is the best hope in achieving this goal. The Air Corps is impressed so far and asks for 3 prototypes to be built. The plane's future, however, comes crashing down with its first prototype. A stalling malfunction results in the first Ascender taking a 16,000-foot nosedive. As the company attempts to fix this problem, competing technology is evolving faster than XP-55. In the end, the project is cancelled indefinitely. It is not worth either the government's time or money to further pursue such a risky endeavor. Despite its name, in the end, the plane does nothing but descend into the depths of aviation history. By 1945, as Japan enters the 4th year in its war against the United States, the sleeping giant that Admiral Yamamoto feared would awake is now on his nation's doorstep. After massive casualties on both sides, American military power is successful in pushing back Japanese forces through both its superior air and sea power. The American mainland remains untouched after Pearl Harbor, with military production skyrocketing. Japan, a nation that seemed invincible in early 1942, is now feeling this incredible American force wreak havoc over its mainland. In particular, Japanese cities and their inhabitants feel the horrors of an air war that does not distinguish between military and civilian targets. American B-29s, leaving from the islands of Guam and Saipan, fly a total of 107 bombing raid missions on Japan's cities in just 1 year. One particular raid that takes place on the night of March the 9th destroys 250,000 homes and burns almost 100,000 citizens to death. In General MacArthur's historical report, he writes that the effect of these raids rocked the nation to its very foundations. With each passing month, the casualties keep escalating, with nearly 3 million people killed. Mass famine is spreading, with an estimated 10 million people suffering from serious malnutrition. Japanese Admiral Matomi Ogaki, writing in his diary on June the 18th, asks, "Does the enemy intend to destroy all of the cities in this country?" General Curtis LeMay, a key architect of this bombing strategy, pledges to bomb and burn them until they quit. The only problem for LeMay is that with a schedule of approximately 16 burn jobs on urban industrial areas every 3 to 4 days, by mid-August, American bombers will run out of cities to destroy. Japanese air forces are proving incapable of preventing this mass destruction of their homeland. A carrier raid in March of 1945 results in 161 out of 193 Japanese aircraft being shot down by American forces. Vice Admiral John S. McCain pledges to hunt down and destroy every damn plane in Japan. Despite the much-feared kamikaze tactics being employed by Japanese pilots, American military leaders are no longer planning the possibility, but the eventuality, of Japan's surrender. The maps being used by both the Joint Chiefs of Staff and the President show that whether it is through a ground force invasion or through the dropping of an atomic bomb, Japan is a nation on the brink of defeat. The only decision being made by the political and military leaders of the United States is which course of action they should embark on in order to achieve the goal of an unconditional surrender. To those Japanese military leaders who are in their last throes, their hope is to develop a highly maneuverable interceptor plane to act as an antidote against American B-29s. The Shinden aircraft, developed by Kyushu, is the only aircraft with a canard designed to be ordered into quantity production during the Second World War. Equipped to hold one pilot and having a wingspan of 36 feet, armed with 4 30mm cannons and a top speed of 466 miles per hour, in addition to its important canard features, the Japanese military is hoping that Shinden holds the answer to solving the problem of the B-29 bomber. Work begins in June of 1944 to develop this plane, whose name translates to Magnificent Lightning. By now, however, time is not something Japan has on its side. Although the first prototype of the Shinden flies on August the 3rd, it is simply too late to prevent a devastating American attack. 3 days after it is tested, the first atomic bomb is dropped on Hiroshima. 3 days later, the city of Nagasaki is dealt the same blow. With these two bombings, in addition to the Soviet Union declaring war against Japan, the demand of unconditional surrender is met on September the 2nd, 1945, marking the end to war in the Pacific. The story of the Shinden remains one of the greatest what-ifs in Second World War history. Had Japanese production and testing begun earlier, would this aircraft have been able to stop American bombing plans as hoped? If the jet technology for this aircraft arrived in time, would the Shinden have been to Japan what the Spitfire and Hurricane had been to Britain in its time of need? For it remains an unknown piece of canard history. The canard design, with its origins dating back to the Wright brothers and their first flight of 1903, is a story of aviation constantly having to overcome the barriers and obstacles put in its way. It is a story of emerging and innovative technology locking horns with the politics of its time. Whether it is a result of a new government taking power, the policies of production, or of a country in desperation, canard technology never soars above these barricades in the first half of the 20th century. There is no doubting, however, what canard technology represents in the history of aviation. It symbolizes the innovative spirit, and it symbolizes the proud heritage of aviation. The canard design is to be remembered through its planes and by the people that created them.
The Miles aircraft concern conceived the M39 Libellula during the early 1940s, amid the turmoil of World War II. Initially, the concept aimed to simplify landing aircraft on carrier decks, addressing visibility challenges caused by forward-mounted engines and large wing mainplanes. A novel tandem wing arrangement was pursued to mitigate risks, resulting in a series of concepts explored by Miles during the war. The overarching term for these Miles designs was Libellula, named after the taxonomic family of the dragonfly. The groundwork for this project began with the M35, essentially a technology demonstrator for a single-seat naval fighter. Miles pursued this endeavour independently, using the tandem wing setup to reconfigure the centre of gravity found in conventionally configured military aircraft. In a brief span of 6 weeks, Miles engineers introduced the M35. This aircraft was equipped with a single de Havilland Gypsy Major air-cooled inline engine, boasting 130 horsepower. During testing, the engine exhibited temperamental behavior and longitudinal control was problematic. Nevertheless, this design provided valuable insights into the unconventional arrangement, contributing to future developments in the field. Building on this knowledge, a new design emerged, scaled at 5/8 and designated as M39B. This single-seat demonstrator featured a pair of de Havilland Gypsy Major IC air-cooled inline engines, each with 130 horsepower, showcased in outboard nacelles beneath the rear wing mainplanes. The frontal mainplane was now positioned low against the sides of the cockpit, and the fuselage boasted a finely contoured shape from nose to tail. The undercarriage transitioned to a traditional tricycle configuration. Given the larger scope of the M39B project, its dimensions were appropriately increased. The wingspans now measured 25 feet at the front set and 37.5 feet at the rear. The overall length extended to 22.3 feet, and the maximum weight rose to 3,200 pounds. As constructed and tested, the M39B achieved speeds of up to 166 miles per hour, thanks to its twin-engine setup and tandem wing approach. The maiden flight for the M39B occurred on July 22, 1943. A dorsal fin was later fitted at the fuselage aft for additional control to complete the M39B's iconic three-finned appearance. Up until September of 1943, all of the work on the two aircraft, M35 and M39B, was as a private venture. From then on, the British Air Ministry decided to offer a formal development contract to Miles. Shortly after, Miles sought interest from the United States Army Air Forces, aware of their consideration of the domestic Curtiss XP-55 Ascender, which shared a tandem wing pusher engine configuration and was intended as a fighter. The USAF's response revealed a general lack of interest in the Miles product, as the XP-55 itself faced issues, particularly with stalls and recovery. The American program only progressed to flight testing, producing 3 aircraft in total. The M39B underwent evaluation at the Royal Aircraft Establishment, encountering problems from the outset. A new undercarriage had to be installed, and several accidents necessitated constant repairs, keeping the aircraft grounded for extended periods. Despite its unconventional arrangement, overall handling characteristics were considered normal. While landing and takeoff required adjustments to the standard routine, these were deemed forgivable, and stalling and recovery performed as anticipated. In 1941, the RAF issued a new specification for a medium-class, medium to high-altitude, high-performance bomber. Miles responded with its M39 project, a modified version of the M39B featuring a pressurized cockpit for a crew of 3. The proposed power for the M39 project included either 2 Rolls-Royce Merlin 61 series inline engines or 3 Powerjets W2500 gas-powered turbine engines. This design featured a significant wingspan increase, measuring 37.5 feet at the frontal wing and 55.8 feet at the rear pairing. The overall length expanded to 35.9 feet, and the maximum weight surged to 26,750 pounds. The envisioned cruising speed was 360 miles per hour, and armament was planned to include 2 20mm cannons in the wing roots, 1 gun per root, along with an internal bomb bay in the fuselage, capable of carrying up to 6,000 pounds of bombs. Ultimately, the de Havilland DH-99 Vampire fulfilled the specified requirements. The Hawker P1005 also competed for a period. Although a prototype M39 high-speed bomber was ordered under a November 1943 contract, it was never constructed. The RAF's bomber needs were met elsewhere, leading to the termination of the M39 project, along with the data-collecting M39B aircraft. While surviving the war, the M39B lasted only until 1948, when it was scrapped. Despite its shortcomings, the Miles Libellula left an indelible mark on aviation history. Its bold, unconventional design inspired future aircraft engineers to think outside the box and take risks. The Libellula remains a testament to the power of human ingenuity and the boundless potential of innovation. The Miles M39B Libellula serves as a fascinating case study of a daring, experimental aircraft that ultimately fell short of expectations. Its unique design, ambitious goals, and ultimate cancellation offer valuable lessons for future aviation endeavours.
During the course of World War II, German aircraft designers embraced many unusual concepts. Some worked, but not all. The Blumenvoss P-163, a product of the mind of Richard Vogt, a German aircraft designer who conceived of many weird and wonderful designs during World War II. At a time when the shortage of aluminum was starting to affect aircraft production, the P-163 concept offered a way of partially utilizing steel as an alternative, at least in a limited way. Of course, there would be a weight penalty. However, the additional strength of steel might allow the wings to support a crew gondola and each wingtip, thereby allowing much more free space in the main fuselage for engines, weapons, and fuel. Each of the gondolas would have weighed about 1 ton. Vogt predicted that they would actually improve flight performance by reducing both bending in the wings and turbulence from their outer edges. Project 163 was envisioned as a high-speed bomber, fulfilling some of the multiple roles performed by the famous Junkers Ju-88. The Junkers plane was clearly in the fast bomber class. It had a crew of 3 or 4, grouped together to improve morale and enable better communication. However, the aircraft was lightly armed and relied mainly on speed for survival against enemy fighters. In contrast, the design of Blumenvoss's new proposal necessitated having 2 separate crew seating positions, separated by at least 60 feet. The 163 was manned by a crew of 4, with 2 men in each gondola. There would be a single pilot who would have a spectacular view, not disrupted by turning propellers. More significantly, the pilot sat back to back with his navigator and part-time gunner, who was in an excellent position to cover the rear and left flank of the aircraft. To balance the architecture, Project 163's other gondola had 2 gunners, one facing aft, the other forward. At least in theory, this high-speed bomber would have been very well protected. Not surprisingly, there were serious concerns about the actual control of such a revolutionary layout. How would a pilot react to being at the very tip of an aircraft rather than the center? To test the impact of this position on the pilot, an early asymmetric Vogt design was modified. An additional gondola was added to the BV-141's port wing and tested. Another major advantage of the wingtip cockpit was that it would leave the 163's main fuselage less cluttered, leaving space for a power plant that consisted of 2 engines coupled together, driving counter-rotating propellers in a center-line thrust. At about the same time that Project 163 was being developed, the center-line thrust approach was also being explored in the south of Germany by the Dornier Company. Their DO-335 Arrow heavy fighter bomber design was also based on the principle of center-line thrust. One engine set in the traditional nose position, and another placed in the center of the fuselage, driving a propeller at the very back of the aircraft. In the United States, another company, Douglas Aircraft, were also engrossed in another center-line thrust project, which was just as revolutionary. The XB-42, or Mixmaster, was designed as a fast, long-range bomber. It employed 2 engines mounted near the middle of the airframe, driving separate propellers grouped together at the rear. The XB-42's layout, like that of the DO-335, resulted in extremely clean flying surfaces that made for increased speed and maneuverability. Both aircraft were finally made, and with testing so advanced, they probably would have gone into production if the war had continued. Meanwhile, back in Germany, the war was not going well, and the benefits of all new aircraft projects were being seriously reappraised. Although it was reasonable to assume that Blumenvoss had a design that would be the equal of the Junkers Ju-88 in speed and range, and it would also have offered considerably more defensive gunnery, there was still caution about the practicality of the crew positions. How would pilots feel about such an unusual design? The acid test would be the adapted 141 asymmetric plane. The standard BV-141 actually worked quite well. The addition of yet another gondola at the very tip of one wing made the aircraft even more bizarre looking, but it served its purpose and apparently proved that the wingtip cockpit arrangement was workable. However, workable just wasn't enough. Project 163 was cancelled before a prototype was built. There would be no armadas of this unusual-looking aircraft flying over enemy targets, and the addition of another gondola at the very tip of one wing did not turn it into a swan. But it served its purpose and apparently proved the wingtip cockpit arrangement was acceptable. Another factor behind the decision to cancel the 163 was its performance. It simply did not offer any major improvement on what was already proven and available. But performance was not Richard Vogt's primary objective in designing the 163. His goal was to find a way of substituting steel for aluminum, which at the time was in short supply. But as the war progressed, not only aluminum, but all materials in Germany were in short supply. But Richard Vogt's revolutionary concept would later be vindicated by the United States Air Force. In 1949, the Northrop F-89 Scorpion was finally selected by Air Defense Command as its mainstay all-weather interceptor. It was to be armed with cannons, but the A, B, and C models displayed structural problems in the wings, and there were some losses. In 1954, the D model entered service. This had a much strengthened wing and a huge pod mounted on both wing tips. Each pod contained 52 Mighty Mouse rockets. The F-89D became the main production version of the Scorpion, and perhaps supported Vogt's theory on wing bending and turbulence. The post-war B-17 clearly demonstrated the benefits of Vogt's wingtip theory.
We had a B-17 there that had a crew position on a right wingtip. The reason they did that was to develop central gun control. They had this on the B-29, however it wasn't on a wingtip, but that was what the airplane was built for. However, the war was over and everybody forgot about that, except the Aeromed people thought, oh, what a wonderful thing to find out what it is like to roll an airplane if you're not on the roll axis. Everybody said it didn't make any difference, but they insisted on doing it, and they built a cockpit in that position out there using the formation stick, which was worked through the autopilot, and you could fly the airplane from this position out on the wingtips. I got to fly it. The one thing you did learn was, you know, when you're in turbulent air, you keep seeing the wings flap up and down. That's not exactly what's happening. The wings tips are more or less steady. It's the fuselage that's moving up and down. And you could sit out there on that wingtip and jiggle the formation stick longitudinally and make the people in the airplane sick, and you were hardly moving. But you didn't do it too much because they'd get mad at you and get even with you later.
In recognition of his genius, Richard Vogt was invited immediately after the war to work in America. He contributed to many designs, including the ambitious Tiptoe project and its many variants.
In the post-World War II era, the concept of military aircraft capable of vertical takeoff and landing, VTOL, captured the imagination of designers and military strategists globally. The increasing performance of land-based jet aircraft necessitated longer runways, which in turn presented vulnerabilities. A single conventional bomb on a runway could incapacitate an airbase and its aircraft. Naval aviation faced similar challenges, as aircraft carriers were susceptible to attacks. Despite the number of combat aircraft a carrier could operate, any damage to the vessel rendered its air power ineffective. The idea of VTOL-capable aircraft emerged as a potential solution to these issues. Such aircraft could be launched and recovered from small, temporary forward air bases or even from vessels considerably smaller than traditional aircraft carriers. Recognizing the strategic importance of VTOL capabilities, the USAF and US Navy jointly sponsored Project Hummingbird in 1947. This project aimed to explore and study the practical application of VTOL technology, laying the groundwork for innovative designs like the Convair XFY-1 Pogo that would follow. This project was able to use data captured from Nazi Germany at the end of World War II, and, in particular, design work on a projected German VTOL aircraft, the Focke-Wulf Triebflügeljäger. The Triebflügeljäger was a radical design concept created in 1944 in response to the increased Allied bombing of German industrial targets. Its design never went further than the creation of wind tunnel models, but the concept of a tail-sitter VTOL aircraft captured the interest of the US Navy. They were interested in a fighter that could be launched from any warship and even from transport ships or tankers. The prospect of equipping each US Navy ship with its own point defense interceptor led to a significant re-evaluation of the necessity for vulnerable aircraft carriers. Building on the findings of Project Hummingbird in 1948, the US Navy initiated a more detailed study and, in 1949, sought the expertise of the National Advisory Committee for Aeronautics to assess the feasibility of developing a tail-sitter VTOL interceptor. This concept, resembling the Triebflügeljäger in some aspects, employed a conventional fuselage with an engine driving contra-rotating propellers in the nose. A successful model demonstrated the ability to take off and land vertically, seamlessly transitioning to conventional forward flight. In May 1951, the US Navy awarded contracts to both Convair and Lockheed for the production of 2 prototypes, each of a VTOL tail-sitter fighter. Both the Convair and Lockheed aircraft were slated to be equipped with the powerful Allison T-40 engine, a development based on a pair of T-38 Allison turboprop engines arranged side by side, delivering power to a shared reduction gearbox. This marked a significant step forward in the pursuit of effective VTOL capabilities for naval interceptors. The power of the engine was estimated to be over 5,000 kilowatts. In comparison, the Pratt & Whitney radial engine fitted to the Vought F4U-4 Corsair, then in service with the US Navy, provided around 1,700 kilowatts. The pilot's seat was able to rotate through 45 degrees to allow it to be used comfortably in both vertical and horizontal flight. No armament was ever fitted to the XFY-1, but this was expected to take the form of either 4 20mm cannon fitted in the wing's outboard of the massive propellers, or a pack containing 48 folding fin unguided aerial rockets. The first XFY-1 prototype reached completion in early 1954 and underwent testing in a fixed vertical stand at Lindbergh Field in San Diego. The performance in this setting was satisfactory, prompting the decision to proceed with the next phase of development, involving tethered and untethered flight testing. The second prototype was transported to NAS Moffett Field near Sunnyvale, California, where a specially designed tethered test rig was set up in the colossal Hangar No. 1. This historic hangar, originally constructed in the 1930s, once housed the US Navy airship USS Macron. The rig featured a motorized reel attached by cable to the XFY-1 propeller hub, providing a means for emergency reeling to swiftly return the aircraft to an upright position. The challenging task of determining whether the XF-Y-1 could actually fly fell to Lieutenant Colonel James F. Skeets Coleman, a US Marine Corps Reserve pilot and engineering test pilot for Convair. Tethered flights were conducted with assistance from Convair flight test engineer Bob McGreary, who controlled the tether mechanism, ready to pull the XF-Y-1 upright in case Coleman lost control. Coleman faced the daunting responsibility of testing an aircraft that was both radically different and potentially hazardous, making his role as a test pilot exceptionally challenging. In November 1954, Lieutenant Colonel James F. Skeets Coleman achieved a significant milestone by executing the first transition to horizontal flight in the XF-Y-1. Remaining in conventional forward flight for over 20 minutes, he safely returned the aircraft for landing. The XF-Y-1, powered by significant thrust in a compact and streamlined airframe, proved to be remarkably fast. Even with throttles at their minimum setting, the aircraft cruised at speeds exceeding 300 miles per hour. During level flight, it often surpassed the conventional chase aircraft assigned to monitor its progress. The absence of speed brakes or spoilers made landing at these high speeds particularly challenging. To address this, Coleman developed a unique landing technique. Approaching the landing field at around 300 miles per hour, he would pull the stick all the way back when close to the landing point, causing the XF-Y-1 to enter a vertical climb. As the speed decreased, he carefully added power until the aircraft reached a hover at an altitude of around 1,000 feet. Then, while looking over his shoulder at the ground, he gently reduced power during the descent. The XF-Y-1's lack of stability in the hover demanded constant control corrections during descent, especially as it encountered turbulence from its own reflected prop wash near the ground. One of the most demanding aspects of landing involved judging the aircraft's rate of descent within safe limits, a task requiring the pilot's attention to the ground over his shoulder and continuous control input to maintain stability. The unique characteristics of the XF-Y-1 demanded exceptional skill and precision from its pilot during the landing phase. As an aid, Convair mounted a small radar altimeter pod on the left wingtip. This was connected to 3 lights in the cockpit. Green meant that the aircraft was in a stable hover, amber meant that it was descending within safe limits, and red meant that the rate of descent was too fast. Even with this device fitted, the XF-Y-1 was a fiendishly difficult aircraft to land. Coleman was clearly an exceptional pilot, and when another US Navy pilot was allowed to fly the XF-Y-1 for the first time in May 1955, he was lucky to survive the experience. The XF-Y-1 never took to the skies again, and the project officially concluded in August 1956. Lockheed's XF-V1 tail-sitter II was abandoned without achieving vertical takeoff or landing. From a strictly technical standpoint, the XF-Y1 demonstrated success. It executed numerous flights, showcasing its ability to fly conventionally and to perform vertical takeoffs and landings. In this limited sense, it marked the first successful military VTOL aircraft. However, as a potential operational aircraft, the XF-Y1 faced insurmountable challenges. Landing safely was an exceedingly difficult task. Lacking automated flight stabilization in the hover, it demanded constant corrections from the pilot, who also had to closely and continuously monitor descent rate, position, and attitude. The second critical issue leading to the project's cancellation was performance. By the mid-1950s, jet interceptors capable of exceeding Mach 1 were being produced. In just a few years, operational aircraft would achieve Mach 2 capabilities. Despite the formidable power of its turboprop engine, the XF-Y1 could never reach even Mach 1. This limitation placed it at a distinct and insurmountable disadvantage as a combat aircraft, making its operational viability untenable in the face of evolving technological standards.
Lithe, graceful, and deadly, the pterodactyl was one of the first known reptiles that evolved powered flight. Its wing movements held within them a beautiful science that would live on long after the end of the prehistoric world. But out of the remnants of that distant past, one 20th century inventor created a method of flight that would change aviation's future. In the designs of Geoffrey Hill, the swept-wing tailless plane would not fly as a machine, but in the same style as a living animal. And the pterodactyl would find life again in a new man-made body, but would soar above the earth just as it always had. The dust had barely settled from the Second World War when Allied forces started to exploit the treasure trove of aerodynamic data collected by the defeated Luftwaffe and its various manufacturers. Britain too followed suit in sharing the spoils of war. Many German aviation concepts were seriously considered and in fact ultimately employed. At the same time, the British government could sense the onslaught of the Cold War and wanted to be ready in case tensions between the US and the Soviet Union suddenly turned hot. The nation was deeply in debt, but Homeland Security was still given top priority, which is why the British Ministry of Supply issued an order for a new bomber. History would later call this order the V-bomber specification. The government was looking for a long-range aircraft that would employ the jet power technology discovered but not used to its full capacity during the war. Coupled with the aerodynamic marvels developed by the Germans, Britain was determined not to be caught off guard in the event of a nuclear conflict. The Americans had already shown the might of their atom bomb at the end of the war, while the Soviets got a jump start on their own program by exploiting German nuclear resources.
The best recent study by David Holloway on Stalin and the bomb has come to the conclusion that the Soviets were really disappointed at the sort of technological level of the German nuclear program, and that the chief gain for them was not the sort of technological know-how of the German scientists, but the uranium, the processed uranium that they managed to get their hands on, which in Holloway's estimation probably saved the Soviet nuclear bomb project about a year.
Britain was developing its own bomb program and felt the first things it needed were bomber aircraft advanced enough to carry the load. 4 submissions from 4 different British manufacturers were ordered to go into production. 3 of the planes employed technology that was borrowed from newly accessible German research. Because of them, history would look back on this era as the golden age of British bombers, where grace, beauty, power and efficiency were all ingredients used to produce the majestic aircraft of Britain's V-bomber force: the Vickers Valiant, the Avro Vulcan, and the Handley Page Victor. Of these 3 bombers, the Valiant had the least sophisticated design, but was the first to see flight time, with a prototype taking off in 1951. This was a conservative but cleanly built aircraft and could accommodate a 10,000-pound bomb. In fact, the very first British atomic weapon, a live Blue Danube, was dropped during a 1956 test in Australia using the Valiant B-1. Despite being the least advanced of the V-bombers, the Valiant was the first to fulfill the purpose for which it was built. In contrast, the Avro Vulcan was a sleek subsonic bomber and sported a unique delta wing configuration that set it apart. Its wingtip rudders gave it control even while carrying 21,000 pounds worth of bombs. Of all the V-bombers, the Victor was regarded as the most futuristic and avant-garde in both looks and performance. Because it was specifically designed to quickly invade Soviet airspace, it could fly higher and faster than any of its contemporaries. Despite the defense capabilities these 3 planes gave Britain, it was interesting that none of them was 100% British. Each had its origins in the seized German research. There was, however, the 4th V-bomber submission that the government rejected as being too ambitious. It was the Short Brothers PD-1, a medium-range bomber design that had very little to do with seized German technology and more with a single flying wing. To help create this advanced aircraft, the Shorts team recruited an engineer who was famed for his work in tailless plane design, Professor Geoffrey T.R. Hill. Despite Hill's involvement, the PD-1 never made it past the design stage. But it did later take on other forms and names before claiming its place in the books as the Shorts Sherpa, a highly developed unit that sported a unique swept-back wing design that Hill specifically created for this project. The fact that both the Sherpa and the PD-1 had their roots in wholly British research made it ironic that the Ministry of Supply declined to produce the PD-1. This research began a full generation before the other V-bombers were even drawn up. In fact, it was spearheaded by Hill in the 1920s as a series of tailless planes called pterodactyls, aircraft designed for superior flight safety and control. But in spite of Hill's achievements as a pioneer of swept-wing, tailless flight, and in spite of his role in the development of the PD-1 and the Sherpa, he was ultimately disregarded by the aviation community towards the end of his career in the 1950s.
At that time, he might well have been a forgotten man, inasmuch as none of his designs had been taken up. But I think that's only part of the story.
As far as I know, in the later part of his life, he was desperately disappointed that all of the work and the really brilliant and inventive work that he had done had not really apparently got real tangible results, although there were aeroplanes coming out of Short Brothers that were important.
Hill believed that a swept-wing, tailless aircraft represented a more natural method of flight. But he wasn't the one who started the movement. It all began in the early 1900s with a pilot and designer named John William Dunn, whose work greatly influenced Hill. Dunn's goal was to develop a flying machine that required no steering. He designed aircraft for Britain that always bore the distinctive V-shape of an arrowhead, later to be known as swept wings. The original Dunn biplane was such an achievement that almost a full century later, a Canadian mechanical engineer named Barry McKerracher built a full-sized replica of a later version called the Burgess Dunn. Now permanently on display at the Royal Canadian Air Force Museum in Trenton, the plane is the spitting image of the 1914 Burgess Dunn, from the pilot's seat to the copper gas tanks to the airframe. But the plane's swept wings were its most revolutionary feature.
This particular airplane would not fall or stall. As it lowered its airspeed, it actually dipped the nose down, picked up speed, and then came back up again. It didn't fall off to either wing, which is some things that happen to straight normal biplanes or wings.
The idea would change conventional aviation, but Dunn had a hard time proving it. Almost a decade and 4 limited prototypes later, the military had had enough of Dunn's seemingly quirky planes. Spurred on by financial support from his friends, he built and successfully flew the Dunn D5 tailless biplane. Dunn soon built more prototypes, including the smooth and stable D8, which is what caught the eye of an American boat and aircraft builder named Starling Burgess. After Burgess bought the US manufacturing rights, the Burgess-Dunn biplane began its development. Its full wingspan was 47 feet, but the fuselage itself was only 26 feet long. There were 2 seats up top for the pilot and navigator, with the seat in front guaranteeing a particularly thrilling ride. There was absolutely nothing in front of the pilot except his own feet. The seaplane was about 11.5 feet tall and rested on a large float on bottom, making the whole fuselage look something like 2 canoes connected with piano wire and wooden planks. The aircraft was designed with control and handling components to add to its inherent stability. This was so the plane would appeal to military buyers, as it did to the Canadian government. During the First World War, the Burgess Dunn became the first military plane Canada ever purchased. But a rocky delivery prevented it from ever getting airborne.
They got to Quebec City, they didn't have time to take the airplane apart. So they put the airplane on the top of the deck and tied it down so tightly that it wouldn't move. Well, if you get in a rolling sea, things had better move or they're going to be in, and it's exactly what happened at about, I'd say, 100 miles out or on a rough sea, and the airplane just broke up.
Nevertheless, the plane's purchase was a triumph of epic proportions for John W. Dunn, who was once believed to be a failure, but will forever be remembered as the creator of the very first swept-wing, tailless aircraft. While Dunn's journey of producing his plane was finally coming to fruition during World War I, Geoffrey Hill's journey in the aviation industry was just beginning. While on his honeymoon at the end of the war, he happened to look out onto a pond nearby at seagulls on the water. He couldn't help but notice how the birds could achieve a variety of gliding positions without ever losing control of their wings or flight path. Wouldn't it be ideal, he thought, if an aircraft's wings could adjust to the airflow around it, just like the wings of a bird? He soon got the chance to put his newfound inspiration to the test, and, fittingly enough, it took on the name of a prehistoric bird, the pterodactyl. After a brief stint working as a test pilot, Hill won a 3-year research scholarship, which gave him free rein to develop his ideas. Living just outside Farnborough at that time, he spent his days outside building his very first prototype by hand. His wife, May, also helped out by stitching canvas for the wings and lending her husband a hand when he needed it. One day in 1923, the president of the Royal Aeronautical Society, Colonel Alec Ogilvie, dropped by with a financial vote of confidence for the struggling engineer.
And he came and sat in the kitchen, and he said to Geoffrey, "How are you off for money?" And Geoffrey said, "Pretty short. It's getting pretty short, sir." So Colonel Ogilvie reached in his pocket and produced a £50 note, and that was big money in those days. And he said, "Will this help?" "It certainly will, sir," my father replied. Colonel Ogilvie said, let me know how you get on, because I want to come and watch you fly it." And Geoffrey said, "Well, there are plenty of other people who might like to fly it." And Colonel Ogilvie said they're all absolutely scared stiff that they're going to be chosen to fly it, and they're unhappy about whether it will fly or not. So Geoffrey said, "Well, we'll see, and I'm prepared to be the first to fly." So that was really the story of the pterodactyl Mach 1.
Hill stayed true to his word to be the first to fly the aircraft. He first got it airborne on New Year's Eve of 1924 and tested it again several times throughout the following year. It was soon ready for the King's Cup Air Show, where the unusual creation caught the eye of both the King and Queen. They thought it was curious that the aircraft looked so much like a bird, and were even more interested to see how it flew. And they weren't the only ones who were impressed when it took to the air. The head of Westland Aircraft at that time was Sir Ernest Petter, who didn't just notice the pterodactyl because it was oddly shaped, but because it was the one plane in the show with no tail. In almost no time, Hill was named Westland's tailless aircraft designer, and the family moved into a house in Yeovil, which would be their home for the next 8 years. Hill's home away from home would be the Westland facilities, where he was immediately put to work on the Westland Hill Pterodactyl 1A. It was a 2-seater monoplane with a greatly streamlined design and a 75 horsepower engine tucked in the back. Over the course of 1926 alone, this aircraft made 21 test flights and could reach a maximum speed of 70 miles an hour. Despite his flying experience, Hill was told by Westland to stay out of the cockpit and instead get back to the drawing board to devise a new and improved Pterodactyl II, which was designed as a pusher biplane. All of Hill's early models sported wingtip controls that were a combination of ailerons and elevators, namely elevons, which were common on several tailless swept-wing planes in that era.
What they call ailerons on this particular airplane are actually elevons, as there is no tail and no elevator, and the ailerons are back behind the fuselage, so they incorporate the two words and call them elevons. The purpose, of course, is to raise or lower the nose of the aircraft or turn right or left.
The pterodactyls did not use surface controls like ailerons in a normal sense. Rather, they would turn at the end of the wing, which was a process known as wing rotation. Only when both wingtips moved in opposite directions did they function as ailerons. When they moved in the same way, they would work as elevators. This was the secret behind the pterodactyl's remarkable stability and control. In the early 30s came the Pterodactyl IV, which was a 3-seat cabin monoplane with 120 horsepower and a new tandem wheel undercarriage. This model boasted even better control than its predecessors because it was fitted with vertical rudders instead of the usual horizontal rudders. There was also a new gear installed that made it easy to manually vary the aircraft's wing sweep. While Hill was still planning the Mach 5 version, the Air Ministry specification for which the pterodactyls were built was cancelled. Hill paid no mind to this small setback and continued designing. But the seemingly small setback would be followed by a much larger one.
Well, what happened was that Sir Ernest Petter appointed his son Teddy, aged 26, to be technical director, and it led to my grandfather and others resigning. Essentially, from my grandfather's point of view, he felt that it was quite impossible to develop an experimental aeroplane with somebody with so little understanding of what he was doing in charge.
Coincidentally, Hill received an offer from University College London of a professorship in the Department of Mechanical Engineering. He took the job, but remained a part-time consultant at Westland as a favour to Sir Ernest Petter. However, this arrangement ended when he learned of the blow Teddy dealt to the pterodactyl project.
It was Teddy Petter who actually wrote to the War Ministry, as I understand it, to suggest that the pterodactyl program should be scrapped, and so it was. And I think that my grandfather, it was a really bitter blow to him. By that time, he'd really devoted anything up to 15 years of thinking about how to design a plane in this way, and I think he must have felt that it had come to nothing.
Teddy Petter wanted the company to go after more lucrative government contracts instead of spending time and money on independent research. That decision may have hurt the pterodactyl, but was a shrewd business move that was ultimately good for Westland. The first specification the company pursued after Teddy took the helm in 1934 was for a military observation plane, which gained notoriety as the legendary Westland Lysander. Now that the pterodactyl's development was abandoned, Hill dedicated himself to teaching at University College London for the rest of the 30s. But he again got the chance to employ his tailless principles on an aircraft when the British government sent him to Canada for 2 years during the Second World War. The Allies did not have the upper hand in battle in 1942, and the UK felt it needed better technology. So the Ministry of Supply assigned Hill to a glider project at the National Research Council in Ottawa, where he designed and tested another tailless aircraft. Informally called the NRC Pterodactyl Glider, it clocked about 105 hours in the sky by the end of its testing period, and travelled 2,300 miles, clear across Canada. Although Hill was technically based in Ottawa, his work took him all over the continent. In fact, Hill did a lot more than his official job title suggested, and for employers other than the Canadian government.
He was known as the Senior Scientific Liaison Officer. He was very proud of the title because he said it doesn't mean a thing. So I asked him, what did it involve? And he said, well, I go around the different aircraft manufacturers and help them with their sums. Helping with their sums was really a cover-up, because all the time he was working with Boeings, and they were thinking ahead long after the war. Where do we go to from here?
While working with American manufacturers, Hill met another pioneer in flying wing technology, Jack Northrop, and built a solid rapport with the American aircraft engineer. Focusing on the flying wing was a wise instinct for both men, as the high-wing, tailless monoplane style of aircraft was poised to make a comeback. Although Hill's talents were not always appreciated by the aircraft companies in his native land, the Americans were quite taken with his skills and knowledge. This led to a lucrative offer at the end of the war that would have completely changed Hill's professional life.
My mother suggested that Boeing's wanted him to join them as their chief designer at the end of the war. And certainly I believe there were conversations about that, and he was trying to entice, but he would have unlimited travel for him and his family between the UK and Seattle. And of course, had he worked for Boeing's, the world would have been his oyster in terms of his ability to develop ideas. And so inevitably there is a sense, that here was a really remarkable man.
But Hill could not bear to leave Britain for good, even if turning down Boeing was a terrible career move. Upon returning home at the end of the war, Hill was promoted to Dean of the Faculty of Engineering at University College London. By this time, the war was over, but tensions in Europe were still simmering. Germany was still a hotbed for political trouble, and the presence of the Soviet Union in that country did not help the situation. With this in mind, Britain's Ministry of Supply issued requirements in 1947 for an advanced bomber that would protect its interests should the need arise. These requirements for a very complex and cutting-edge aircraft were later known as the V-bomber specification. However, the ministry recognized it would be difficult for most manufacturers to quickly fulfill this need. So it also put out a more simple order for a conservative World War II-style bomber that could carry a heavy load and be built much faster. Short Brothers of Ireland won the bid to make this four-engined aircraft called the SA-4 Sperrin, which looked more like a product of the Second World War than a contender to fly in the Cold War. The ministry thought so too, but only years later, when two prototypes were already in the works. Shorts was formally told that the Sperrin would not go into production, but its prototypes could still be completed and tested. At about the same time that Shorts was drawing up plans for the Sperrin in 1947, it was also readying itself to relocate to better facilities in Belfast. In addition to taking on the Sperrin, the company decided to also bid for the extremely advanced bomber aircraft that the Ministry of Supply initially ordered. This plane would be the technological opposite of the Sperrin in appearance and capabilities. But the company still needed an expert in aeronautics to help guide the process. Hill's principles were quite well known in the aircraft industry, and Shorts felt he was the right man to call for this job. Despite his distinguished position at UCL, he tendered his resignation and made the move to Belfast. He was technically a consulting engineer for Shorts, but oversaw several projects that others were creating. He also worked closely with chief designer David Keith Lucas, who shared Hill's great interest in tailless plane design. The fuselage of the new aircraft would more or less be modelled after the Sperrin, but the rest of the plane would be far more innovative. They proposed a flying wing configuration, so all the controls would be found on the single wing. Curiously enough, the highly swept wing coincided quite closely with German data for aircraft which could only really maximize the feature at high speeds unobtainable without jet power. By this time, jet power was being employed by at least 4 different countries. With the availability of the jet and ready access to high-speed wind tunnels, Short brothers used Hill's basic premise of the pterodactyl, invented almost 30 years previously, to research and design a concept known as the PD-1, a medium-range, high-speed bomber capable of carrying a weight equivalent to those of that era's atomic devices. The wing on this aircraft would still be swept, but would bear differences from the wing that Hill put on the pterodactyl series several decades before.
Jeffrey called it the isoclinic wing, which meant that you could alter the pitch of the wing at different speeds, that if an aircraft was coming into land, it could have the full use of like a fixed wing, but when it got up high, it could fold it, not completely fold it back, but a few degrees, and this would improve the performance enormously.
Short's PD-1 proposal competed with at least 3 other prime contesters, the basically conservative Vickers Valiant, and 2 highly advanced designs, the Avro Vulcan and the Handley Page Victor. Both the Vulcan and the Victor employed German aerodynamic technology, while Short's aircraft was entirely built upon British research of the flying wing. Short's held the title of being the oldest aircraft manufacturer in the world, and was very well respected within government circles and the industry. But on balance, it was ultimately felt that the company's revolutionary design was perhaps a little too revolutionary, and so it was rejected, while the other 3 aircraft went on to form a triad that became Britain's V-bomber force. Not to be deterred, Short brothers continued privately in 1951 with the development of their 1/3 experimental glider model of the PD-1, which was called the SB-1. This glider was the first aircraft that actually featured Geoffrey Hill's aero-isoclinic wing, and was designed to be an inexpensive machine, which was a good thing, because the only prototype crashed after just a few months of testing. Hill and Keith Lucas went back to the drawing board and emerged 6 months later with an aircraft that essentially sported the same design, but now had a lighter fuselage and 2 small turbojets. The rotary wingtip controls remained, as they would provide this new aircraft with greater stability at transonic speeds. This plane was known as the SB-4 Sherpa, a unique design that could trace its ancestry directly back to the pterodactyls of the 1920s. The Sherpa was first flown in 1953 and ushered in a whole new era of flight engineering. But that wasn't all it represented. This test flight brought with it vindication for Geoffrey Hill, who spent a lifetime trying to prove the worth of the tailless plane and the isoclinic wing. This was a lifetime wrought with personal and professional battles to progress a way of aircraft design that was very much ahead of its day. But as far as Hill was concerned, it wasn't at all about personal glory. It was really only about seeing a good idea get recognized.
I think he never personally pushed himself to be recognized. He would never sort of say, what a good boy am I. No, he was very reticent of taking any personal praise. He would take the attitude that gets in the way of progress.
It seemed the very thing Hill had been waiting for was the Sherpa to touch the sky. When it finally did in 1953, he retired. By that time, the once vigorous engineer found his life was slipping into decline, both in terms of his health and the way he was regarded in the aviation industry.
A story that sort of encapsulates this was told by Harold Penrose, again the chief test pilot at Westlands, in I think it was 1954-55, at the Farnborough Air Show. My grandfather always had a drinks party to which he invited all his old friends and so on. And Harold Penrose was running very late for getting there, but eventually got there and was very dismayed to find that there were no cars in the driveway. Anyway, he rang the bell. My grandmother answered it, and he said, "I'm so sorry, I'm late for the drinks party." And she said, "Nobody came, and Jeffrey's gone upstairs to bed, but he'd love to see you." And that was the last time that Harold Penrose saw my grandfather before my grandfather died.
In many ways, it could be said that Hill was a disappointed man when he died in 1955 at the relatively young age of 60. For such a prolific engineer and designer, none of his planes ever made it into production, not even the Sherpa, which was only ever meant to be an experimental aircraft. Moreover, the project he had devoted most of his young life to, the pterodactyls, was cut short before reaching fruition. But at the same time, Hill's goal was finally realized as the Sherpa first graced the skies in 1953. Although it was never a V-bomber, it proved the performance value and stability of the tailless plane, and truly showed the world the importance of the aero-isoclinic wing. And although Hill was never a celebrated designer, it can't be denied that his work altered the flight path of aviation.
The F-12, Trisonic Long-Range Improved Manned Interceptor. Capable of sustained supersonic cruise at more than 2,000 miles per hour. A two-man crew, pilot and fire control officer, fly at altitudes above 70,000 feet in a combat radius greater than 1,200 nautical miles. The airframe and engine design are optimized for Mach 3 flight. The titanium airframe surviving temperatures in excess of 600 degrees Fahrenheit. The two J-58 engines producing 65,000 pounds combined thrust, equal to 4 Century Series fighter engines. Airborne, the F-12 acts as a freelance hunter-killer. The autonomous ASG-18 fire control system, a pulse Doppler clutter-free display designed to operate in any ECM environment, is backed up by 3 Block 3 AIM-47As with an aerodynamic range 20 times greater than present air-to-air missiles. An onboard computer guides the pilot to a collision course in the horizontal plane. The fire control officer monitors a self-contained inertial navigation system, feeding constant positional information to the computer. The horizontal tactics indicator displays interceptor-target relationship in an extrapolated attack, acts as a navigation aid, and provides self-test instructions for the fire control system.
Missile preparation completed. Missile is good. Abbott tracking, range 75 miles. Maximum launch range in 40 seconds. Roger. The dot is set. Well to fire. Special weapon enabled. Roger. Switches are on. Roger. Range 45 miles. Firing now.
Designed to fire at the F-12's optimum cruise altitude with only gross steering required by the pilot, the semi-active pulse Doppler guided missile with conventional or nuclear warhead speeds on a collision course at Mach 6. Aerodynamic range, 100 nautical miles. Sea level to 100,000 feet. Maneuverability, 22 Gs. Up, down, right or left. Complementing the radar is the infrared search and track subsystem. Infrared energy is gathered at long range, allowing early detection of supersonic targets.
IR target confirmed. Better check on our commitment. Army control, this is Alpha X-ray 02. Have an IR target 30 degrees left. Should we hit it?
Alpha X-ray 02, that is affirmative. Freelance approved. We'll have a subsonic track for you within 10 minutes.
The F-12's ability to act as a free agent or respond to precise ground control, combined with its speed and maneuverability, give it a multiple commitment capability over a wide area of NORAD. Worldwide, the F-12 can fly across the Atlantic without refueling in little more than 2 hours. From the United Kingdom, its combat radius covers all of Europe. For Far East deployment, F-12s could make the 7,200-mile trans-Pacific flight to the Philippines in 5 hours with just 2 refuelings and be effective in combat over a wide area. The YF-12A has been flying successfully for a number of years, logging several hundred hours. Even better performance can be expected in the production model. The airframe is a duplicate of the SR-71, an outgrowth of the original YF-12A program. Removing ventral fins and extending chines forward improve aerodynamic stability, increase fuel capacity, and gross takeoff weight. Additional fuel and improved engines extend the ferry range. Payload is increased to 4 missiles. Folding fins allow internal installation, and a trapeze rail launcher permits checkout of 85% of missile functions before launch. A new antenna provides significantly more detection range, more than 100 nautical miles against a medium bomber target. And infrared system performance is improved. The F-12, holder of 9 world records, truly represents a giant step forward in aircraft technology and performance. The first titanium airframe, first sustained supersonic cruise, first pulse Doppler clutter-free radar, and a fire control system designed to operate autonomously. With long-range, highly maneuverable missiles fired from optimum cruise altitude at trisonic speeds, in a performance envelope many times greater than our present capability, the F-12 stands ready today to meet the air defense needs of the 1970s and beyond.
F-92A Convair Model 7002 is a research airplane, a part of the XF-92 program. It is presently being flown at the U.S. Air Force Base, Muroc, California. The purpose of these flights is to gather data concerning the characteristics of a new configuration designed to meet the requirements of an interceptor fighter operating at transonic and supersonic speeds. Extensive study and research by Convair engineers some time ago led to the conclusion that the best aerodynamic configuration for this type of operation was one utilizing a 60-degree delta wing. The wing planform promised several major advantages. First, low drag at transonic and supersonic speeds. Second, smooth handling characteristics and freedom from buffeting at transonic speeds. Third, satisfactory low-speed handling characteristics. And fourth, a structural form ideal for attaining high rigidity, lightweight, and simplicity. Numerous tests of models in wind tunnels and in free flight have confirmed these conclusions. Full-scale confirmation, however, is essential. The Model 7002 airplane was constructed to obtain these full-scale data. It has a 60-degree delta wing and a similar vertical surface. The airplane is powered at present by a single J-33A-23 jet engine with 5,400 pounds thrust for takeoff. Although this is less thrust than is obtained from more recent power plants, it does permit exploration of the airplane's characteristics at high subsonic speeds in level flight. Still higher speeds are obtained in dives. To establish correlation between theory and practice for this new wing planform, a flutter study is being conducted as a part of the program. A major problem in the design of all aircraft capable of transonic speeds is that of providing satisfactory control forces. The 7002 utilizes a 100% hydraulic boost system with no feedback. The pilot senses stick forces which are produced by an artificial field system. Forces are made to vary automatically with airspeed. Pilot comments during flight tests are taken on a wire recorder. An oscillograph and movie photo panel installed in instrumentation compartments comprise the other principal means of recording test data. Perhaps the most outstanding characteristic of the 60-degree delta wing is the low drag rise encountered at transonic speeds. A comparison of the increases in drag coefficient of conventional swept-back wings and that of a 60-degree delta wing near Mach 1 is presented here. The maximum value of the drag coefficient C sub D for the conventional wing is approximately 4 times that of the delta wing. Even more significant is a comparison of thrust requirements in the transonic and supersonic speed ranges. It will be noticed that the difference in speed between the 35-degree swept wing and the 60-degree delta wing is small at the lower values of thrust. However, at the higher thrust, representative of future power plants, the advantage of the delta wing becomes very impressive. Airplanes with conventional tail configurations experience a reduction in elevator effectiveness on approaching Mach 1, whereas a delta wing with integral control surfaces does the opposite. This means that the maneuverability of delta wing aircraft will not be objectionably diminished at transonic and supersonic speeds. Another advantage of the delta wing is that gusts produce lower structural loads. Presented here in graphical form are comparisons of the effects of negative and positive gusts of two intensities. Flight at supersonic speeds with the best turbojet power plants now being developed is practical only when wing thickness ratios are 5% or less. At 5% thickness, the wing weight per square foot of a delta wing is less than half that of a conventional wing with sweepback. Simplicity of construction inherent in the delta configuration is demonstrated by a comparison of the aerodynamic control surfaces required. The controls in the pilot's compartment are conventional. Elevons form the wing trailing edge and move up and down together to produce elevator action when the stick is moved fore and aft. When the stick is moved from side to side, one elevon moves up, the other down. This provides aileron action. Pedals control the rudder, which operates in conventional manner. Initial flight of the 7002 was made at Muroc Air Force Base in the latter months of 1948. In such testing, precise scheduling of operations is required. Other test projects utilize the same facilities. Coordination of all test activities is performed by the Air Force. Before the airplane is taken from the hangar, film is inserted in the instrument recording cameras, batteries are charged, and numerous other items are serviced or inspected. In order to have full tanks for flight, the airplane is towed to the runway before the engine is started. The pilot, flight inspector, and other project personnel necessary to the performance of a flight leave for the runway. Air-to-ground radio communication is maintained throughout test flights. A radio truck receives and transmits pertinent information to observers spaced along the runway. Wind velocity and direction are measured immediately before takeoff. Prior to the first extended flight, a number of high-speed taxi runs and straightaway flights just off the runway were made to provide data for adjustment of the control sensitivity. These runs allowed the pilot to become familiar with the airplane's handling characteristics and to develop the technique of flying at the high angles of attack associated with low aspect ratio wings. The first tests were conducted on the 7-mile lake bed runway. Subsequent flights have been carried out from time to time on the main concrete runway and the shorter lake bed runways. The combined efforts of the Air Force, the NACA, and Convair have been devoted to the launching of this new type aerial weapon. The first takeoff is uneventful. A chase plane is used to make close-up visual and photographic observations of the airplane and its behavior in flight. The two pilots maintain contact by radio. Movie cameras within the fuselage record control movements, airplane attitude, throttle setting, speeds, pressures, temperatures, in short, every aspect of the flight. Approximately 1,500 pounds of instrumentation is carried. This represents more than 10% of the airplane's gross weight. The gross weight at takeoff is about 13,500 pounds. The fuel burned in a 30-minute flight reduces the weight to 12,000 pounds for landing. Completion of the first flight marks the beginning of a period of adjustment, calibration, and research testing. Records must be removed, reproduced, and studied before another flight. The study, planning, and preparation of instrumentation for each flight takes much more time than the operations connected with flying. Limited tests to date show lower drag and higher performance than predicted. Difficulties encountered up to the present time all appear to have reasonable solutions. No problem has yet arisen which compromises the basic advantages of the delta wing configuration. This airplane is the one design now flying in which a pilot can operate transsonically with no undesirable aerodynamic disturbances. With the inherent low drag and good aerodynamic characteristics at transonic and supersonic speeds, the Air Force now has a weapon which can be developed tactically with confidence.
Throughout the 1950s, major aircraft manufacturers in the United States were eagerly exploring the potential of vertical takeoff and landing (VTOL) technology across various military applications. With the looming threat of intercontinental ballistic missiles and thermonuclear weapons, the military sought VTOL aircraft capable of operating from small dispersed sites without relying on traditional air bases or aircraft carriers, targets that were increasingly vulnerable to attack. A key concept driving this pursuit was the notion that an aircraft with a thrust-to-weight ratio exceeding 1 could vertically launch, transition to horizontal flight for mission execution, and then return for a vertical landing. Such capabilities promised to eliminate the need for expensive and easily targeted runways, enhancing the aircraft's survivability and operational flexibility in a rapidly evolving strategic landscape. Among the pioneers in this endeavour was the Ryan Aircraft Corporation, which endeavoured to translate this concept into a practical fighter aircraft for the Air Force with its X-13 Vertijet. However, like most other VTOL aircraft, the performance compromises made for their unique capabilities did not warrant its introduction in place of more capable conventional aircraft. The idea for the Vertijet originated just after World War II, when engineers for Ryan casually debated whether or not their FR-1 Fireball, which had a thrust-to-weight ratio of 1 at low fuel quantities, could take off vertically. The vertical takeoff idea soon advanced beyond the discussion stage. In 1947, the Navy's Bureau of Aeronautics enlisted Ryan for a contract aimed at exploring the technical complexities associated with developing a vertically launched jet fighter, a pivotal aspect of a broader initiative to assess the viability of submarine-based aircraft. Concurrently, the Navy funded a series of experimental tail-sitter aircraft comprising conventionally configured planes outfitted with large counter-rotating propellers designed to rest vertically on reinforced tail sections. Notable examples included the Convair XF-Y1 and Lockheed XF-V1, intended to utilize their high-thrust propellers for vertical takeoff from various naval vessels, thereby furnishing defensive air cover without the need for aircraft carriers. Ryan's engineering analyses demonstrated the feasibility of a comparable jet-powered design, augmented by a reaction control system capable of redirecting exhaust gases to facilitate control during hovering and low-speed flight. Subsequently, a Navy contract facilitated the construction of an unmanned flying prototype, which conducted its inaugural flight on October 20, 1950. This peculiar contraption, affectionately dubbed the Beast in the Backyard, was propelled by an Allison J-33 turbine and employed a ball-mounted nozzle to provide reaction control while hovering. Ryan engineers converted a B-47 fuel tank into a cockpit to allow test pilot Peter Girard to evaluate the testbed's suitability as a manned research aircraft, which sat on its tail to take off vertically. On November 24, 1953, Girard made the first manned hovering flight in a jet aircraft with this unusual machine. After Navy funding ran out, the Air Force became interested in Ryan's experiments and in July 1954 issued a contract to the company to construct 2 VTOL tail-sitter demonstrators designated as the X-13 Vertijet. This project, based on the earlier Navy design proposal, was to demonstrate the suitability of easily dispersible VTOL fighters. Under the guidance of Chief Engineer Curtis Bates, the X-13 emerged as a compact, single-engined delta-wing fighter, with its distinctive features being a set of winglets and fixed landing gear, elements that might appear ordinary to the casual observer. Spearheaded by Robert Furman and the Ryan Technical Section, the aircraft was meticulously designed to be transported on a specialized trailer, capable of tilting vertically to facilitate the launch and recovery of the X-13 during vertical takeoffs and landings. In late 1955, Ryan successfully completed the first Vertijet, serial number 541619, and on December 10th, Girard piloted its maiden flight. Initially equipped with a fixed tricycle landing gear, the X-13 underwent testing as a conventional aircraft. Furman and his team prioritized exploring the conventional handling characteristics before risking vertical flight testing. Following the resolution of oscillation issues through the installation of dampers, engineers affixed a temporary steel tube truss with custering wheels to the rear of the X-13. This modification allowed the aircraft to assume a tail-sitting position during vertical flight testing, eliminating the need for the complex launch and recovery procedures associated with the launch trailer. Pete Girard made the first vertical takeoff and landing on May 28, 1956. On the same day, the second X-13 made its first flight. The aircraft was agile and responsive in conventional flight. As the aircraft transitioned to a nose-high attitude to achieve a hover using the thrust from its own engine, a vectorable exhaust nozzle linked to the controls provided a straightforward and efficient means of control. To facilitate the delicate landing process, small bleed air thrusters positioned on the wingtips enabled minor adjustments to the pitch and yaw of the aircraft when necessary. Integrating both conventional and VTOL control systems, a stability augmentation system ensured smooth transitions without requiring abrupt changes to pilot control inputs. During vertical takeoff, the launch procedure involved raising the bed of the launch trailer vertically. This allowed the X-13 to hang from a cable suspended by two arms on the top of the trailer, featuring a partially retractable hook. For vertical operations, flat bumpers replaced each of the main wheels on the fixed landing gear, preventing damage to the fuselage underside if it swung into the trailer bed, thereby facilitating transportation. Subsequently, the pilot would increase throttle until the hook lifted off the launch cable, then maneuver away from the trailer and accelerate vertically, smoothly transitioning to conventional flight. However, vertical landings posed greater challenges and were perhaps the most impractical aspect of the vertijet concept. Its primary drawback, akin to earlier tail-sitters, lay in the obstruction of the pilot's vision by the airframe, making it exceedingly difficult to accurately gauge the distance to the ground without external assistance. Although the pilot's seat pivoted 45 degrees towards vertical during landing, the pilot still had to approach the recovery trailer blind, with the underside of the fuselage facing the surface of the trailer. Constant radio communication with a ground observer was essential to talk the X-13 into position during the cumbersome process. A 6-meter, 20-foot long folding pole with marked gradations attached to the top of the recovery trailer gave the pilot a clear indication of the distance remaining before he contacted the trailer. Once in position, the pilot gradually reduced the throttle until the nose hook caught the recovery cable. On May 28, 1956, the X-13 executed its inaugural vertical hovering flight, initiating a series of summer tests where Girard and fellow test pilot Lou Everett practiced cable catching techniques using a 1-inch thick rope strung between two towers. To safeguard against potential damage during docking maneuvers with the trailer, Ryan engineers equipped the X-13 with a replaceable wooden nose. On November 28th, Girard accomplished the first ever transition from horizontal to vertical flight and vice versa in the X-13. Then on April 11th, 1957, he launched from the trailer, seamlessly transitioning to conventional flight, and executed a vertical landing, successfully fulfilling the X-13's mission profile. Illustrating the concept of dispersed operating sites, the second X-13 captivated over 3,000 military officers and journalists with an impressive display at the Pentagon on July 30th, 1957. However, competing programs diverted funds away from the project, leading to the X-13's final flight on September 30th, 1957. Despite later programs like the XV-6 Kestrel and the AV-8 Harrier achieving operational success, the X-13 provided an effective solution to the challenges of developing a VTOL fighter within the technological constraints of its era. The Vertijet successfully completed all designated tasks and undoubtedly excelled as an experimental demonstration aircraft, despite the inherent impracticality of the operational concept. Ironically, by the close of the 20th century, the thrust vectoring system, originally pioneered on the X-13, would evolve into an indispensable component of advanced combat aircraft. In 1960, Ryan generously donated the first X-13 along with its launch trailer to the Smithsonian Institution.
During the early stages of the Cold War, and before the advent of guided missiles, the West had to rely heavily upon jet-powered fighters to ward off Soviet bombers. For some time, the only effective armament for these fighters were barrages of unguided missiles.
One of the changes that took place in the 1950s involved air-to-air weapons. It had been traditional until then that combat airplanes would carry machine guns or cannons. And everyone knew and everyone said that fighters need guns, except when they didn't say that. And they didn't say that when they were talking about defending the United States against bomber attack. They designed several types of interceptors that used partly or entirely unguided air-to-air rocket projectiles.
At first, each interceptor would just have one opportunity to fire in a gunshot approach with a weapon from a bygone war. The B-29 was more expensive to develop than the atom bomb. It was so complex to build that some manufacturers are said to have taken on other projects just to avoid being selected to assemble this most advanced flying machine. Even Boeing didn't really want the task of building their own creation. In the end, the Army Air Force took over much of the management, although Boeing, Bell, and Martin still had to deliver. The B-29 was cloaked in secrecy throughout its early development. Occasionally details were released, but this was really disinformation to confuse the enemy, who by 1944 had seen enough of the superfortress to fear its destructive capability. In one such subterfuge, a single B-29 was landed near London to convince the German High Command that many other B-29s were to follow. The result was that Germany took extensive precautions to counter the superfortress, although none were necessary as the United States never planned to attack Germany with B-29s. The war against the Japanese Empire was a very different matter. Japan was the target that the superfortress was conceived and built to attack. Rushed into service, many early B-29s flew over Japan with technical problems, particularly with engines overheating. One safe haven for a damaged and struggling superfortress was the Soviet port of Vladivostok. At this time, Russia was not a combatant with Japan. In fact, it was technically a neutral power that could not give support to either the United States or Japan. At least 3 B-29s were forced to land in Vladivostok. They were promptly seized, repaired, and flown to Moscow. Just before the Japanese surrendered, Russia declared war on Japan, which made them a US ally in the Pacific. But Russia still refused to return the 3 B-29s. American wisdom was that a superfortress would be technically too sophisticated for Soviet engineers to replicate. And that view prevailed for several years, even as the Soviet relationship deteriorated from ally to enemy. However, in 1947, at Moscow's annual Aviation Day parade, 3 B-29s appeared overhead. At first, Western observers assumed they were American, but opinion quickly changed when a 4th identical aircraft appeared. Soviet engineers had obviously developed a clone. This was bad news on the aviation front, but worse still was the knowledge that the Soviets had for some time breached Western security and had gained access to atomic secrets. The Los Alamos project alone had at least 3 Soviet spies in its workforce. In August 1949, the Soviets, in an exercise known as First Lightning, detonated their first atomic bomb. The news shocked the West. Soviet possession of the atom bomb and the means to deliver it demanded an effective response. However, most Western air forces at the time were still flying fighters from World War II. Anticipating the nuclear threat, in 1946 a new air defense command had been formed for the aerial protection of the continental United States. At first, the ADC had to rely upon a stalwart Second World War night fighter, the Northrop P-61 Black Widow. The aircraft offered some radar capability, long-range and all-weather endurance, but most important of all, it was available. Later, an unusual derivative of the successful P-51 Mustang, the P-82 Twin Mustang, was pressed into service. The original P-82 was envisioned as an escort fighter. It was fitted with radar and served as an ADC interceptor. However, neither of these aircraft had the speed of a jet, and they relied upon machine guns or cannons, neither of which were likely to be very effective against a B-29, wherever it was built. Having designed the Superfortress in the first place, the US knew only too well its defensive capability. The task of successfully downing a B-29 had been given to German engineers some years earlier, when the Nazi hierarchy were tricked into believing that superfortresses would be used over Germany. The Wehrmacht's answer came in the form of the A4M rocket. The rocket had been developed from an artillery missile of slightly less than 3 inches diameter and had 8 folding fins. These would be fired in a salvo at an oncoming American bomber. The salvo approach was necessary because the rockets lacked accuracy. Allied intelligence had been aware of the A4M's devastating effect when they hit a target, especially when coupled with the speed of an Me-262. Against this arrangement, the Allies had no answer.
One of the weapons that really, I think, would have been a very frightening thing if it had gone much further was the Me-262 armed with the R4M rocket missiles. Now, they had 2 batteries or 2 racks of 12 in each wing, and they were used right at the end of the war. Not in a great deal, but when they struck a bomber, it wasn't a question of damaging it, downing it, it was a question of disintegrating the entire thing. It was, a hit was total destruction.
The technology was really quite basic. In the 262's case, the launch platforms were basically carved out of wood. Other German interceptors using the A4M were fired from a simple metal tube nicknamed the stovepipe. Apart from the A4M's motor, the only other technology it employed was its folding fins, which snapped open after launch. FW-190s and Me-262s were adapted to use Germany's new rocket defense. However, there was one aircraft that was built around the A4M, extremely ambitious and reflecting the desperate state of the Third Reich. The Bachem-Natter's sole reason for existence was to deliver the deadly folding fin rocket. The Natter used a chemical-driven Walter rocket as its main motor. 4 solid-fueled rocket power plants aided its vertical takeoff. Bachem's design only flew on one occasion and killed its young pilot in the process. But knowing of its deadly potential, Allied ground troops were to prioritize the capture of anything to do with the A4M. Fast forward to 1949. NATO gives Russia's clone nuclear bomber the codename Bull. By this time, some of America's first-generation Air Defense Command jets were close to delivery. Many of them were developed for use with two valuable assets that would help reduce the Soviet threat. Firstly, the US had improved on the A4M concept with the introduction of a four-finned 2.75-inch rocket that would ultimately be named Mighty Mouse, after the popular cartoon character of the time.
Quite a few of the aircraft projects in the 1950s did away with the gun. It was thought the gun, and in other words, close-in fighting was no longer required. It would be air-to-air missiles. But you can only carry a small number of missiles at the time. And so an alternative to the gun was the unguided rocket. In America, the version was known as the Mighty Mouse.
Airborne radar was also coming of age. First employed at the end of World War II, it was now ready for use in conjunction with ground radar. Radar was particularly important when employing fighters known as interceptors, as they are required to fly at night and in all weather conditions. In 1945, the US Army Air Force was preparing to enter the jet age and had asked for submissions for a jet-powered night fighter to replace the propeller-driven aircraft it then had in service. A serious contender for this contract was the Nighthawk, a four-engined dual-seat interceptor from the Curtiss-Wright Company. The Nighthawk's failure to perform in flight tests in 1948 led to the demise of the Curtiss-Wright Company. Instead, Air Defense Command chose a contender from Northrop. The F-89 Scorpion had two engines for safety and dual seats, one for a dedicated radar operator. The Scorpion was to be equipped with cannons because Mighty Mouse was not yet available. Delays in delivery of the F-89s had the advantage of enabling them all to be fitted with folding fin rockets. In fact, the Scorpion could carry 102 of the rockets.
The F-89, which was quite an interesting aircraft with big rocket pods out on the end of the wing, and pretty heavy aircraft, but the usual case that we've done in so many of our aircraft, by the time we get through hanging things on them, they're all underpowered. and the F-89 didn't last long, but it was one of the airplanes in the air defense development that took place as we moved into the Cold War time frame and our expectations that we might have to fight Russia.
However, late delivery of the F-89s at this very sensitive time in history led Air Defense Command to order two other interceptors as immediate backup. Lockheed calculated that they could convert the T-33 trainer to a two-seat interceptor using up to 75% of the Tu-33's parts, a major saving in money, and more importantly, time. ADC was very impressed, as the first flight of the XF-94 was made just 3 months after the contract was signed. The latest C version of the Starfire carried Mighty Mouse rockets, just as they were starting to become available. The second backup for the Scorpion was a North American aviation project. The company's F-86 Sabre had been a major step forward in fighter design, but it was primarily a dogfighter, not an interceptor. But North American believed that the basic frame could be converted into the interceptor role. In the event, only about 25% of the original F-86 parts were used to make the F-86D or Sabre Dog. Nevertheless, their unit cost was around 1/3 of the twin-engine Scorpion. Nearly all the 2,800 F-86Ds that rolled out of North American's plant were armed with the Mighty Mouse rocket. Like the Nazis' Bacher-Natter interceptor rocket, it existed solely for the purpose of delivering 2.75-inch folding-fin rockets.
The F-86D didn't have any guns. The F-86D Sabre carried a tray of these rockets under the pilot. The tray had to be extended, then the rockets could be fired.
There was another interceptor that would be armed with the folding fin projectile, the Canadian CF-100.
We had 2 rocket pods, 29 rockets each, and so there's 58 total, and it was a one-shot effort. So when you were into a bomber stream and locked onto the bomber, you would fire these things off, and it was essentially a shotgun type approach. You're bound to hit something. One rocket would do the job.
Canada's Arctic region required an all-weather aircraft. Like the Scorpion and the Starfire, the CF-100 had a 2-seat configuration with a dedicated radar operator in the rear. Working in conjunction with a string of early warning radar posts, almost 700 CF-100s were built. They served for almost 30 years. So important was the project that Avro Canada cancelled its promising early jet airliner design to concentrate on its rocket-firing defender of North America. Eventually, Mighty Mouse rockets were superseded by supersonic surface-to-air missiles like the Boeing Mach. Army Nike shorter-range anti-aircraft missiles took over much of the air defense roles in the mid to late 50s. Air Defense Command did retain the use of some Mighty Mouse rockets on its new generation interceptor, the F-102 Dagger, but only as support for the Falcon-guided missile, which was the Dagger's primary weapon. As guided missile technology improved, the Mighty Mouse was no longer able to compete for a spot on board U.S. interceptors.
Unguided rockets. They didn't have very much range. They were unguided, and of course the moment you fired them, they were under the effect of gravity, so actually getting them to actually hit a target, anything beyond a very short distance, was really not much chance. And so needless to say, by the 1960s, this weapon wasn't carried very often at all.
During the Vietnam War, the 2.75-inch rocket was paired with armed helicopters, and it was reborn as a ground attack weapon. Literally millions of Mighty Mouse rockets were launched against North Vietnamese targets from a wide range of U.S. rotary and fixed-wing aircraft. Specialized warheads could be fitted onto the rockets depending on their intended end use, be it anti-personnel, anti-tank, or basic target marking. During the Gulf War, the Apache helicopters that opened the air campaign by destroying 2 Iraqi radar sites with Hellfire missiles also carried Hydra 70 rockets, the modern-day incarnation of the Mighty Mouse. The folding fin rocket was born out of the Reich's desperate need to stop the flow of Allied bombers devastating its territory. When faced with the possibility of nuclear annihilation by Soviet bombers, the US grabbed onto this German weapon and adapted it into their own Mighty Mouse. Those surface-to-air missiles and air-to-air missiles would relieve the Mighty Mouse of its intended mission of knocking down Soviet bombers, the folding fin rocket would find new life as a ground attack weapon, a mission it still carries out to this day.
In 1938, Luftwaffe Chief Hermann Göring declares, "I completely lack the bombers capable of round-trip flights to New York with a 5-ton bomb load. I would be extremely happy to possess such a bomber, which would at last stuff the mouth of arrogance across the sea." 4 years after that statement is made, the nation of Germany begins to feel the industrial strength of America firsthand.
bombers begin pounding the Nazi regime day after day with attacks from England. With the United States means of production out of reach, any hope of retaliation seems impossible. Little do American leaders know that 3 planes are being developed in order to do just that. Messerschmitt 264, Junkers 390, and Focke-Wulf TA-400 are being rushed into production to make it across the Atlantic in order to reciprocate this destruction. It is a project cloaked in secrecy for more than 70 years. Many details are sketchy, based on hearsay and unsubstantiated claims. Now take an in-depth look at both the planes and the possibilities they represented. Could they have tipped the scale in favor of the Axis so late in the war? Could they have actually made it across the ocean and back without refueling? Explore alongside historians and experts the story of the America bombers. On December the 11th, 1941, Hitler declares war against the United States of America. Ever since the Second World War has begun, the two nations have been battling it out unofficially in the Atlantic Ocean.
Hitler probably declares war on the United States because there's already an undeclared war going on against the United States of America. In the North Atlantic, with U.S. destroyers, U-boats. So he may think it's simply inevitable. But whether he thinks it's inevitable or not, it probably wasn't, and it's a terrible mistake on his part.
We came in the war because of the Japanese, because of Hitler's stupid agreement with the Japanese. And he lived up to his agreement, but it really did cost him the war. You know, if he'd never made the alliance with Japan, you know, we might be doing this interview in German.
Before Pearl Harbor, America supplies the Allies with war materials, causing its ships and German U-boats to clash as a result.
It is quite clear that the United States had broken their neutrality at least 6 months before Pearl Harbor by assisting the British in getting the convoys from the United States to Britain safely and without being attacked by German submarines. So there was actually this warlike activity already in existence between American destroyers and German submarines without there being a public state of war.
Just prior to Pearl Harbor, there are a series of incidents in the North Atlantic. 3 destroyers are involved in altercations with German U-boats. The Greer, the Kearney, and the Reuben James. And there's an escalation with each one. And with the Kearney, it's merely an exchange of fire. There's a torpedo fired at the Greer after a U.S. plane takes a shot at the submarine. With the Kearney, the ship is actually hit with a loss of U.S. life. And with the Reuben James, that is sunk. And Roosevelt points to this as a reason for increased vigilance and activity against the Nazis. And it's a question of who fires first and all that.
For Hitler, the decision is an easy one. The United States will no longer be considered neutral. The gloves can finally come off. Its shipping capabilities are now fair game for German submarines. Once victory is declared over the Soviet Union, America and Britain will sue for peace. That is the Nazi plan. In less than a year, however, the exact opposite happens. Fighting against both Japan and Germany, the arsenal of democracy only grows stronger.
The Americans, again, had the resources, they had the industry, they had the time, and this huge industry that could produce trainers, fighters, light bombers, medium bombers, heavy bombers, patrol bombers, any type of aircraft you can think of, and the tanks, and the trucks, and produce the gasoline, and the munitions, and everything else, and the ships, huge navy. They could do all of that at the same time. The Germans couldn't.
Factories begin turning out a plane every 5 minutes, and a ship every day.
American factories were in 24/7 production by the end of 1942, and in 43 and 44 not only armed one of the largest militaries in the world, but armed our allies as well, the British, the Soviet Union. In the course of the war, we gave somewhere around 50,000 trucks to the Soviet Union, 15,000 tanks, 7,000 aircraft.
The United States has a unique advantage due to its geography. It does not have to worry about planes bombing their factories. It can go on producing at an unprecedented level.
America never really gets out of the Great Depression until World War II comes along. The unemployment figures were as high as 17% in the late 1930s, and they really don't start to drop until America becomes the arsenal of democracy, supplying Britain and the Allies and shipping literally billions of dollars overseas. The Lend-Lease program ultimately is $50 billion by itself, which in the dollars of today is about $800 billion, a tremendous stimulus package for the American economy.
They were delivering huge numbers of aircraft and tanks, and vehicles, trucks, etc. to the British and the Canadians and the Australians, etc. So they were a major producer of weapons for the Allies.
And having two oceans protecting its civilian population, the American people are confident that they're providing materials that will shift the balance of power away from the Axis.
Economists say the natural resources of the United Nations are greater, but the capacity of the Axis to turn what resources they have into weapons of war is tremendous. They have the mighty Krupp munitions works. We have Birmingham. They have Skoda. We have Delaware. They have factories like this in occupied France. England has Vickers. They seized the steel mills of Luxembourg. We have Pittsburgh. They have great factories to turn out Heinkels, Messerschmitts, Dorniers. We turn out flying fortresses, P-38s, P-40s, Aerocobras, Tomahawks, many others. Romanian oil drives their planes and tanks. Oil from the fields of Oklahoma, Texas, and California will drive our planes and tanks.
For German leaders, the United States poses a serious dilemma. With more than 5,000 miles separating the two countries, no existing German aircraft can even come close to reaching America's east coast. In early 1942, the only strategy available to Nazi war planners is unrestricted submarine warfare.
One of the most successful weapons that the Nazis had was the U-boat fleet, the U-boat service, the Kriegsmarine, which is essentially, by the end of the war, a U-boat navy. They were in 1942. They were wildly successful. It looked like they were going to just win the war just by sinking everything in the Atlantic.
A plan known as Operation Drumbeat begins with U-boats torpedoing America's shores, sinking millions of tons of shipping.
Well, the Americans, of course, were very much surprised by the immediate reaction or action, not reaction, by German submarines after the war has been declared by Germany. Germany at that particular time sent a group of submarines over to the American coast, and America was totally unprepared for that kind of assault. And the German submarines over there found absolutely no opposition whatsoever, and it was partly a Turkish shoot for them. The ships were illuminated; they were not in convoys. The cities were not blacked out, so it was partly for them almost a peacetime-like exercise they did, and of course they were very, very successful in doing so, and put America into a state of shock from which it took them many, many months to recover.
Operation Drumbeat, or Paukenschlag in the original German, was the first U-boat offensive against the east coast of the United States. And to say that it was a happy time for the U-boats and their crews is understating the case considerably. And in fact, many of them did look back on it as those who survived the war look back on 1942 as just kind of a happy hunting time. It takes all modern nations some time to gear up into a war posture, and it might take democracies longer than dictatorships, and it might take our fractious and argumentative democracy in America even longer than some. And certainly the Japanese bombed Pearl Harbor in December of 1941, and we were at war a couple of days later, but it's not to say we took it with the seriousness that it deserved. And something as simple as blacking out cities on the East Coast was policies and procedures would have to be drawn up. It's not simply a case of everyone in New York turning out their lights at the same time. Now, with illuminated cities along the East Coast, every single American transport which sailed from harbor was nicely silhouetted against a bright background of lights. And U-boat and submarine commanders just could not have had a juicier or more lucrative target. And these experienced crews took advantage of it, sinking somewhere around 2 million tons of shipping in 1942.
Caught off guard, it takes time for American war planners to augment their strategy in dealing with this submarine menace. Through the use of a convoy system, as well as ordering mandatory blackouts, Operation Drumbeat fades away.
The turning point can be placed at early 1943, and in May, I think, when we lost about 40 boats in 1 month or something like that.
By 1943, materials and supplies begin reaching Britain with little interruption. Once on English soil, their impact is felt immediately. B-17 flying fortresses and B-24 Liberators begin flying over the heart of Germany. Alongside British planes, the fatherland is bombed mercilessly.
The offensive continues in greater and greater strength.
Well, certainly German industries took a pounding. German civilians took a pounding. Winston Churchill probably put it best when he once said that the air effort was dehousing the German people, destroying their living quarters one building at a time.
Cities are turned into rubble. And with Soviet victories on the Eastern Front, the Allied powers begin closing in on the Axis. Hitler, seeing the destruction firsthand, is outraged at these bombings. However, with his U-boats neutralized and the United States out of reach, there's little Nazi generals can do to fight back against the American war machine. What is needed is a wonder weapon to enact revenge. Beginning as early as the interwar period, German war planners study a hypothetical attack on the United States.
Dornberger, assisted by Werner von Braun, had been thinking about some kind of a rocket-propelled weapon that could attack the United States as far back as 1937. There was a weapon that they were designing called variously either the New York bomb or the American rocket. It had an interesting intent. They would take a massive booster rocket, put a V-2 at the top of it, fire it off, and the V-2 would eventually attain speeds of 6,000 miles an hour, which meant that it could cross the Atlantic in something like 40 minutes. It could strike New York, it could strike Washington, it could strike Boston.
Of course, you can never laugh these things off because Germans were so innovative that sometimes they achieved things which to many minds were quite impossible.
The Germans were never able to launch any sort of attack on the continental United States. That's not to say they didn't talk about it, they didn't plan on doing it, and they didn't draw up various schemes for doing it, some relatively realistic and some much more fanciful.
Many concepts are examined and many are rejected due to their technological limitations.
There was the notion, for example, of launching a V-1, the so-called buzz bomb, in some ways the distant ancestor of our modern cruise missile, of launching a V-1 from a ramp on the deck of a U-boat that had surfaced off of the American coast. Now, of course, the problem of getting a German U-boat to the American coast with a large ramp and a buzz bomb on top of it was never really dealt with.
Some of these ideas even border on the realm of a science fiction novel.
Likewise, there was a plan for towing a V-2. Now, the V-2 being the not-so-distant ancestor of the post-World War II intercontinental ballistic missile, of taking a V-2, encasing it in its own missile launcher, and then putting it into position on the back of a U-boat. The launcher would swing into a vertical position, that is a launch position, and thus then launch the weapon against an American city, presumably New York, and presumably Manhattan. Now, the problems with such a plan, of course, include getting, once again, that V-2 over the Atlantic Ocean, crawling with U.S. naval vessels of various shapes and sizes, not to mention our own submarine fleet, and doing so while trailing an extremely heavy and extremely obvious 118-foot-long canister without being detected.
The most realistic and achievable weapon is a long-range bomber.
In 1939, things in Europe were not going too well, and war clouds were beginning to erupt. It was then that Hitler realized, and some of the hierarchy in the Luftwaffe realized, that they may need something that could fly a little bit further than what they originally conceived. So they put out a specification to try and get a bomber that might reach the United States.
Attacking the American East Coast with raids the same way the B-17 is attacking the fatherland.
The Germans were very intent on finding some way that they could strike the United States by air. Besides having worked on rocketry, they were also developing a bomber.
So the Germans realized that at one point, if you wanted to stop or at least put a brake on the production effort in the US, you would have to put some threat over their head. The only way to do that would be to bomb them.
Unfortunately for the Nazis, it's a goal that's difficult at best. For a plan like this to work, it must reach America and back without refueling.
The problem that the Germans faced in building a long-range bomber is long-range. It had to go across the Atlantic, bomb New York City, maybe a little slack time there in case they ran into some fighters or something, and then it had to turn around nonstop without landing and fly back to Norway or the west coast of France, which this is a long trip, and nobody does this today. Your 747 doesn't do this today. They'll land in Europe or in England and refuel and check the plane out. They couldn't do this. The Germans couldn't do this. They had no way to land. So if you're going to do this in a round-trip fashion, you have to have a truly intercontinental bomber. And this is something the United States didn't have until the B-36, which was 1949, 1950.
Their best chance is with the Bollemann Voss 222 flying boat. But the odds of it making it back to the fatherland are slim to none.
Well, I flew the 222, and I would certainly agree it could get to within range of the American coast. It was a pretty impressive flying boat. I do not believe that they could ever have attacked the American coast and got away with it, because though it had this tremendous range, and it was nice, quite nice to fly, got quite light handling controls, it was very vulnerable to a fighter attack. And I just don't see it surviving any attack by any fighter at all, frankly.
12,000 miles would be needed in order to strike. No plane during this time can even come close in covering a distance this size. The Germans' longest-range bomber, the Heinkel 177, is encountering numerous problems with its unworkable tandem engine arrangement.
They didn't really get around to building 4-engine bombers, and when they did, it was an off and on type of thing. So one general actually was fired over this idea that he didn't come up with a 4-engine bomber later on in the war, Ernst Udet. He was marginalized and then committed suicide, probably over this very issue.
A plane of this magnitude must instead be designed from scratch.
But they realized it would have to be a very long-range bomber. For all intended purposes, you're looking at the German equivalent of the B-29.
And in order for it to work, an enormous amount of time and material is needed for production, development, and testing, something the Germans are lacking by this time.
There were lies about the stocks of aluminium available. Production had not been rationalized. civilian resources had not been mobilized. And there was still a belief on the part of fighter pilots that quality was what mattered and that you would only get that by producing aircraft in relatively small numbers. So mass production was avoided. In 1944, Britain alone had 12 factories that employed more than 10,000 people. Germany only had 2.
Despite these roadblocks, Adolf Hitler, having a fascination with wonder weapons, enthusiastically gives a green light to the project. The America bombers are born. To provide a buffer of relief, Nazi planners believe they have a perfect halfway point. The Azores, an archipelago of 9 islands located 900 miles east off neutral Portugal, is ideal for a project of this nature.
Now they realized that the distances were huge. Actually, that's why they considered using the Azores as a base. It's halfway across, not quite halfway across the Atlantic, but it's certainly closer than bombing from bases in France. So there was definitely an interest there.
In 1940, after the fall of France, Admiral Raeder strongly urged Hitler to occupy them before the Americans could get to the islands first.
At one time, it was speculated, even Hitler suggested, that perhaps they should invade the Azores and take over the Azores and use it as a jumping off point for their long-range aircraft to fly to the States.
Now, if German planes are given permission to land the same way German U-boats are allowed to dock, this geostrategic area would be worth its weight in gold. Having the range requirements significantly reduced, the plan to bomb America now appears more feasible than ever. What is needed now are targets. In order to cripple the arsenal of democracy, these hypothetical German planes cannot just bomb indiscriminately. They instead must go right after their means of production, attacking factories that are building the planes and bombs that are ruining German cities. Prepared by the War Department in April of 1942, a 33-page document lists 21 potential targets for the Germans to attack. The Aluminum Company of America, located in Messina, New York. The Chrysler Corporation in Detroit. The Wright Aeronautical Company in Cincinnati, Ohio, and many others are the destinations for the America bombers. The targets and the takeoff are set. In looking for companies to build these super bombers, the Nazi regime goes to the very best.
They came up with some designs. Every builder would come up with, every aircraft manufacturer would come up with a design, and they would take a look at the designs on paper and select one.
Messerschmitt, makers of the Me-109 and the 110, 2 planes that battled Spitfires and Hurricanes during the Battle of Britain. It's also the company that's working on the revolutionary Me-262, the first jet-powered aircraft. Beginning in the late 1930s, Messerschmitt begins dabbling in what is known as Secret Project P-1061. Its requirements are for an aircraft capable of reaching bases in Central Africa as well as Vichy French territories. Now, the plan calls for a plane that can reach the United States, carrying a payload of 5,000 kilograms.
Messerschmitt came up with an idea that got off the ground, the Messerschmitt 264, and they originally wanted something like 6 prototypes for testing. And if these were proved successful, then they were going to build a fleet of them.
Awarded the contract by the German government, workers at Messerschmitt begin working on the aircraft known as the Me-264. Different versions are considered, and once the plane begins taking shape, it starts to look eerily similar to another design that's being constructed across the ocean.
So by and large, there were designs. I think there was a Messerschmitt 264, which looks a little bit like a B-29.
The 264 was actually quite an interesting aeroplane design. It had a circular fuselage section, which in stress terms was very, very good, because the circle has equal stress points. It was built over a long period of time, and it didn't actually fly until 1942.
Originally designed with 4 BMW 801G engines, German officials hope that a 6-engine version will be in the skies as early as the fall of 1943. However, designers are noticing that the first prototype of the aircraft has a very high wing load. This is resulting in a loss of maneuverability, an unimpressive climb rate, and in-flight instability. 2 more prototypes are to be tested, one with armaments and one that is to be fully completed. However, with the aircraft being years away from flying, alternative designs and designers are sought out. Junkers, makers of the Stuka dive bomber and the Ju-52 transport plane, present their vision of a transoceanic aircraft capable of bombing Uncle Sam. The company is highly favoured amongst top Luftwaffe officials when it's taken over by the government in 1935, following the death of its founder, Hugo Junkers. Having overseen the company's nationalisation personally, Field Marshal Erhard Milch leans towards the alternative.
Had the advantage of having a roll-on, roll-off capacity for equipment, because it had a rear door that could be dropped. And that was the big advantage. You didn't need to have trucks to load it and unload it. You could actually drive on and drive off. And that was the major advantage of the 290.
The train of thought now is to just enlarge this aircraft for bombing America. The result is the Ju-390, a plane with 6 1700 horsepower engines, a wingspan of 181 feet, and a fuselage that is even longer than the American B-29.
Junkers were actually adapting their Ju-290 aircraft into the Ju-390, which was actually a 6-engined aircraft. And a lot of people, especially the German Navy, thought that would be quite a nice aeroplane, and others thought that yes, it would make a very nice America bomber.
The Ju-390 was a similar situation. There were 2 built that we know of. One was given to Hans Bauer, the Hitler's pilot. So it was for Hitler's use, for state use. So Hitler had a 390.
Built at the Junkers factory in Dessau, the first prototype is able to make its maiden flight in August of 1943.
They had high hopes for this bomber, and between this and the Messerschmitt 264, it looks like that much time, or if not in total time, these were controlled by the SS.
Despite its early success, the Nazi hierarchy still wants an insurance policy. On August the 11th, 1938, the nation of Germany makes history when a Focke-Wulf Condor arrives in New York City after a rigorous 24-hour flight across the Atlantic.
There was still this belief in the USA that they were very safe, and isolationism was still very, very rife there, and that any kind of invasion from abroad would have been almost impossible. However, in 1938 an event occurred which changed all that. This was that on the 10th of August 1938, a Focke-Wulf 200 took off from Berlin-Staaken and flew right across the Atlantic and landed at Floyd Bennett Field in New York after a 24-hour, 59-minute flight, non-stop. This put the wind up senior military people who suddenly realised that they weren't quite as safe as they thought.
Having proved itself capable of flying long distances, the aircraft goes to work during the war, providing reconnaissance for U-boat operations.
The Focke-Wulf 200, it was of course the civil Condor at one stage, and then it was militarized to become the Courier. And in fact, as the Courier, it was very successful as a reconnaissance aircraft over the Atlantic. It was very heavily armed, and it had a wide range, and where it did the damage was it could operate beyond fighter range from the from England or from Britain.
Now, the plan is to evolve the Condor the same way that the 290 is being evolved. The result is the TA-400, consisting of 6 BMW 1700 horsepower engines. Just to keep this monster up in the air, an unprecedented 32 fuel tanks, capable of carrying 7,000 gallons of gasoline, are put on board the aircraft. Possessing a pressurized cockpit, 2 remote-controlled turrets, 20mm cannons, and a payload of 22,000 pounds. The third of the America bombers appears to be the deadliest. As Germany struggles to find a way to attack the United States, many options are looked at. Submarines, space rockets, and espionage are appealing, but the most realistic strategy by 1942 is a long-range bomber. 3 companies, Messerschmitt, Junkers, and Focke-Wulf, all bring their designs to the table and begin working on planes that can render a decisive blow against America.
Russia did not actually capitulate. And in the winter of 1941, it actually launched a counterattack in front of Moscow. And there began a phase of the war which was to last more or less till its end. It was a war of attrition, a war eventually to be on 2 fronts, precisely the war the Germans always knew they couldn't win.
By 1944, the tide has turned in favour of the Allies.
Beginning in 1943, the American Air Force and the RAF, the British Air Force, were mounting 1,000-plane raids against Germany. By 1944, these raids were creating havoc in Germany. 3 raids against the city of Hamburg resulted in something like 50,000 German dead. The cities in Germany were being destroyed, leveled at the rate of something like 2 a month.
While the principles of war remained unchanged, the use of new weapons revised the concept of war. This time, Germany was faced with a weapon that leaped over battle lines and frontiers and smashed at the ultimate enemy, the German worker, who equipped and fed the German soldier. This time, the enemy nation was physically destroyed before its defending army was defeated.
But as the Allies came to rely increasingly on a strategy of strategic air power as a way of bringing Germany low, the need became pressing for some sort of escort fighter, and of course that need was met in the P-51.
The P-38 was available at first, then the P-47. Neither had the range to be able to escort the bombers all the way from England to Germany and back. The P-51 was the first that could do that. So now you had bombers flying raids all the way into the heart of Germany, even as far as Berlin, being able to have a very effective fighter escort the whole way there and back.
In England, Operation Overlord, the invasion of France, is being planned by both British and American generals for later that year.
At D-Day, in the final planning, the head of Allied Tactical Aviation was asked, well, what are we going to do about the German fighters? He said there aren't going to be any German fighters so far. And he was essentially right, because they'd been wiped out by them. So, I mean, you know, it had a huge effect, I think, on the whole course of the war, of being able to bring the fight directly to the German tactical aviation forces.
For a Germany in its last throes, they begin turning to the secret weapons they have invested so much time and money into as the saviors that can strike a knockout blow.
The Holy Grail was a weapon of mass destruction. And they had gone the road of the nuclear, hoping to get the nuclear bomb. They had gone the road of the V1 and the V2. But they were always, as I say, searching for that Holy Grail.
August of 1944, Hitler and Mussolini met in Germany. Mussolini took a train to Germany, and they had a little heart-to-heart talk. Mussolini said to Hitler, look, I've been deposed once, I've been reinstalled in northern Italy. The Allies are in Italy, The Allies are closing in. The Russians are closing in from the east. It's August of 1944, and what guarantee do I have if I still throw in my cards with you, Adolf Hitler, that you can actually pull this war out? Because it's not looking good now. And Hitler said to Mussolini in so many words, "I have some wonder weapons coming."
In Peenemünde, the Luftwaffe is working overtime, getting the V-1 flying bomb ready to launch. And if this device fails, the revolutionary V-2 rocket is going to strike the fear of God into the Allies, being the predecessor of today's intercontinental ballistic missile.
The V-1 and the V-2 were extremely important in terms of later weapons development. The V-2, of course, a single glance at it will make clear that it is the ancestor of the later ICBM, the Intercontinental Ballistic Missile. But perhaps even more than that for most Americans, it is clearly the ancestor of our NASA effort to reach space.
The target for both these weapons is London, where no one will be spared. Britain's ally, the United States, is also set to receive a deadly dose of a different type of wonder weapon.
The Americans were using Great Britain as an aircraft carrier to bomb Germany. Bombing England or bombing London alone, the British may have said no more, but there's no guarantee that the Americans were even going to let them do that at this point. They were so intent upon crushing Germany, and they had the Russians moving in from the east. So for a lot of political reasons, you have to stop this at the source. So the Germans were interested in bombing New York City, number 1, Moscow, number 2, and London, number 3.
In order to strike fear across the Atlantic, the America bombers are being hurried along. As development continues, the Nazi leadership is hoping to get at least one of these planes across the ocean to deliver a fatal blow.
The Junker 390, which was tested in a flight that managed to remain aloft for something like 12,000 miles, which would easily have made a round trip to the United States. And one of the practice runs they ran within 12 miles of the U.S. coast. The Germans even had another bomber in their plans, and that was a Messerschmitt plane, the ME-264. It was also tested and very likely could have struck the United States.
If this plan proves successful, the psychological impact could be the German equivalent of the Doolittle raid.
Yeah, the targets for the ME-264 would obviously have been preferred to be military targets. But the propaganda value of simply dropping a few bombs on New York would have had an amazing effect, both in the USA and on the morale in Germany. In the USA, it would have no doubt caused a lot of panic and created a lot of defensive maneuvers within the East Coast because they didn't know if and when the bombers could come back.
In bombing the United States, the Germans saw that they could politically damage the United States, damage the American leadership so much that the Americans would reconsider their quest for total victory. In other words, that the Germans could do a deal. The Germans could do an armistice on the Western Front and perhaps keep fighting the Soviets. They really didn't like the Soviets. The Americans and the British they didn't, that wasn't part of the bargain when they started the war. They really didn't, they looked upon us as more of a nuisance that got to festered and became a huge problem for them. So they would have always liked to just do away with us and continue fighting the Soviets.
As intelligence leaks, President Franklin Roosevelt and Prime Minister Winston Churchill begin to worry about the secret weapons Germany might have in store for them.
Franklin Roosevelt was very conscious of the capacity of German science. And indeed, in 1944, in December of that year, one of his agents who was posted in Turkey, which was a hotbed of international espionage, reported to him that the Germans had mastered another weapon called the V-3, and that it was capable of attacking the United States. Now, Roosevelt took this threat seriously. In fact, he confided to one of his people that he understood that a single bomb launched in this method could destroy a United States city. So he put the East Coast on alert when this attack presumably was going to happen. Obviously, it did not occur, but it pointed out the potential of German science.
If resources are diverted, England will be softened up for the eventual launchings of the V1 and the V2. The only thing that Germany does not have on its side is time. By 1944, as the America bombers are being developed, Germany remains in a weakened state. Being pounded into submission day and night by Allied planes taking off from the coast of England, and with the Soviet Union moving in from the east, it's no longer an if, but when the Nazis will surrender. Their factories cannot continue unless a dramatic reversal of fortune occurs. Only a miracle weapon can save them, which along with the V1 and the V2 is hopefully the planes designed to pulverize Uncle Sam. However, just as the project begins to develop, the dominoes begin to fall, lessening the chances that one of these planes will make it up into the skies before it's too late. The first of these is the decision by the Portuguese government to lease the Azores bases to the Allies. Sensing which direction the war is going in, the neutral nation turns away from the German plan to launch the America bombers from their territory. This key strategic site, where the Third Reich planned to base these planes, is now only a distant memory. As German cities and industries crumble, Luftwaffe officials are forced to make drastic cuts. In many respects, the America bombers are typical of the hundreds of secret projects being mismanaged that become the Achilles heel of the Luftwaffe.
Right up to the last day of the war, they were working on 138 different guided missile projects. How can a nation which is on its knees be expending effort like this? Fortunately for us, they were expending this sort of effort through total mismanagement and lack of control of their resources.
And one of the failures of the German Luftwaffe was their inability ever to work out a sane procurement and production process. Prototypes would be built and abandoned. They would be rebuilt and altered by Hitler's order and abandoned, and rebuilt a third time and perhaps put into production as an aircraft very, very different from what the original designers had intended. This took place throughout the war, compared to, for example, U.S. procurement policies, which become a giant bureaucracy embodied in the War Department and soon thereafter, World War II, embodied in the Pentagon. The Germans were simply not able to compete on that level.
Only 3 Me-264s had actually been ordered, out of which only 1 was realised, and the other 2 were still in small parts, and nothing really serious was taking place there. And then out the blue, the RLM, the German Air Ministry, asked if they could produce 30 Me-264s. But then everybody realised that where would they build them, how would they build them, and from what would they build them? It was really the boat had been missed on any of that.
The resources, the time, the crews, the ground support equipment, the bases, because you can't base aircraft of that size on a grass field. You need all the infrastructure. You have to get the bombs to the base. You have to get the fuel to the base, and not just once. You have to get the fuel coming back constantly, day after day after day. It's a huge infrastructure that the Americans, the British had to put up in Great Britain. The UK was a giant service station. It's hundreds, thousands of aircraft had to be refueled constantly. That infrastructure did not exist in occupied Europe for a large bomber force. Because sending 2 aircraft every week, what's the point?
With resources strained, planes still in their design stage are now in the crosshairs. One aircraft that's on the chopping block is Focke-Wulf's TA-400. After assessing its design and noticing it requires more labour and materials than the Me-264, the decision to cancel it is made in late 1943.
They investigated and then realised that to actually build it and make it fly would take so many years that it was just impractical to even consider the project as being feasible.
Even as the prototype of the Ju-390 proves to be feasible, by mid-1944 all orders of that plane and the 290 are cancelled.
Again, it would have taken a vast amount of space and material and everything to build. And it really, the performance of the 390 didn't come up to what was expected. So that idea didn't go any further, although the German Navy quite liked the aeroplane.
Now, the only hope is with Messerschmitt.
One was destroyed on the ground. The program was canceled, as all German programs were. There's a start-stop attitude. So it may have been started and stopped several times.
Because of the changing situation of the war, and people had lots of ideas for strategic bombing. One day they were for it, the next day they were against it, and specifications were sort of being issued left, right and centre. Messerschmitt actually did produce a large number of projected modifications to his 264, but none of them ever came to any fruition. I mean, there were ideas to attach huge fuel tanks to the airplanes, which could be 600-gallon fuel tanks carried externally. Also, a 6-engine version was proposed. But all this was real pie-in-the-sky stuff, because none of it could really be achieved at that time of the war. Things were really starting to go bad for Germany, and a lot of this stuff was just panic measures, trying to sort of clutch things out of the air, which really were just not possible.
With the continued bombardment causing a severe strain on the country's resources, Erhard Milch decides to stall production of the 264 and instead focus on the 262. The priority now is defence, and the hope is that this jet fighter bomber can shoot down the flying fortresses that have been pounding them into submission. That same year, several Allied bombing raids on the Messerschmitt factories damage all of the 264s beyond repair. By October of that year, the aircraft is cancelled indefinitely. All of these factors combined spell doom for the America bombers.
This is a solemn but glorious hour. I wish that Franklin D. Roosevelt had lived to see this day. General Eisenhower informs me that the forces of Germany have surrendered to the United Nations. The flags of freedom fly all over Europe.
In the more than 60 years since the Nazi regime was destroyed, many questions surrounding the America bombers program remain unsolved.
When we interrogated William Messerschmitt, he pooh-poohed it as if, I really had nothing to do with it. I think they realized they were going down a blind alley with that, really.
For a project cloaked in secrecy, rampant rumours begin spreading in the decades following VE Day. One such rumour is the assertion that the Ju-390 successfully made a reconnaissance flight of approximately 12,000 miles from occupied France to New York Harbor.
The fact that a Junkers Ju-390 came within 12 miles of New York is something that's said by many sources. It's not just one source. This isn't a wild and crazy guy saying this. This is something that is said and repeated, and I believe to be true.
A hypothetical question asked is, what impact would these planes have had if they were successful in carrying out bombing raids on American cities?
But I would say that even if the Germans could have put 2 or 3 aircraft together that could somehow make that perilous flight across the Atlantic and lob a couple of bombs into lower Manhattan, I think the political impact would have been tremendous. At the very least, President Roosevelt would have been forced to redeploy anti-aircraft assets from Britain, where they were protecting Britain against German air attack, to the continental United States. And that might have had some appreciable impact on the future course of operations in Western Europe.
If the United States had actually suffered on its shores serious damage from German rocketry or from other transoceanic bombers such as they intended, the probably impact on the war would be that it would have been extended. Given the great industrial, innovative powers of the United States as demonstrated in that war by our production, the development of an atom bomb, no doubt we would have struck back, but it certainly would have extended the war to have the destruction brought to our shores.
I wouldn't say a waste of resources, but to a large extent, the hopes of actually curtailing, even annoying the Americans was very small. They might have annoyed them all right, but that would not have been good because the Americans might simply have reacted by bombing the German factories and the bases more fiercely than they did. So in the end, chances are, even that the Germans built the bombers and the bases, they would not have remained in operation very long. They may not even have been completed before they got pulverized.
Would they have been able to crack the well-oiled American war machine by 1945? Would they have been able to weaken civilian morale?
When you look at the effect of the German bombing of England during the Blitz, it's pretty clear it strengthened British resolve. It caused more of a feeling of we've got to get back at those guys rather than fomenting this attitude of, oh, there's no point, we should surrender. So if you're talking about strategic bombing as trying to sap the morale of the enemy, the evidence is pretty clear that doesn't work.
Naturally, the American people probably felt very secure having an entire ocean between ourselves and the war that was raging in Europe. What effect, let's say, on morale would have occurred had the Germans been able to strike us directly? I think it would have been very likely the parallel with London and Berlin. These places were smashed. Berlin was practically reduced to rubble by 1,000-plane raids, but people kept their chins up. They managed to take it and went on from day to day. I don't believe that the American people would have reacted any way differently.
It's very difficult for people who have not been involved in a war like that, or have not gone through the experience, to understand that war to us had become a condition which to us was no more different than the weather. It was something we had to live with. You could talk about it, but you couldn't do a darn thing about it. And the fact that cities got destroyed or submarines got sunk or whatever, it was just part of war. And we took it very naturally somehow without being as dismayed as we are today when we read history.
The plan to bomb America proved appealing to many in the High Command, an act of revenge against a nation that seemed impregnable. Like many other secret Nazi projects, however, a firm lack of purpose and direction existed. The bureaucracy in place at the time and the continued destruction of German factories and cities guaranteed that aircraft like these, despite their potential, would never get off the ground. Instead, these planes and the men behind them remain a pipe dream. One of the Second World War's greatest what-ifs.
Originating from a design philosophy dating back to 1930, but conceived during the Second World War, the XCG-16 glider emerged as one of the most unconventional and innovative glider concepts ever tested. Initially designed for transporting heavy equipment and supplies, including vehicles and military personnel, the XCG-16 later became involved in experiments to deliver fuel to long-range bombers during flight. As a crucial element of the war effort, it showcased the capability to transport substantial loads without the need for an engine. Despite its troubled test history and eventual exclusion from production, the XCG-16's design retained its distinctive features. The roots of the XCG-16 can be traced back to May 1930, when American aero engineer Vincent Bernelli explored various lifting theories and flying wing concepts. the United States Army Air Force subsequently issued a specification calling for a novel design incorporating Bonelli's patented lifting fuselage concept. To assess the most suitable design for military use, a competition among different aircraft manufacturers was organized at Wright Field. Designers Hawley Bolus and Albert Kriz utilized Bonelli's concept as a foundation to create their own glider for the competition. Bolus, previously focused on designing leisure aircraft and recreational vehicles for the civilian market, ventured into military aircraft design for this competition. His most notable design had been the Bolus Road Chief, the trailer and caravan upon which Airstream had based their famous design. He'd also worked as one of the consultants on the Spirit of St. Louis, the aircraft piloted by Charles Lindbergh, who completed the first non-stop transatlantic flight between New York and Paris. Despite lacking experience in combat and military design, Bolus moved forward with his concept, collaborating closely with Kriz and the team at his company, Bolus Sailplanes. The German military's successful use of gliders during the 1940 invasion of Belgium, particularly in landing troops in challenging areas behind Belgian lines, drew attention. Gliders played a crucial role in capturing strategic sites, exemplified by the rapid overrun of Fort Aben-Amal in May 1940, where glider-borne Nazi soldiers surprised Belgian troops. While the United States initially maintained neutrality in the early stages of the war, experiences like the Battle of Fort Aben-Amal prompted the United States Army Air Corps to take gliders seriously into consideration. In response to the USAC's request for a glider capable of transporting troops, heavy equipment, and supplies towed behind engine-driven bombers and transport planes, Bolus and Kriz diverged from the traditional single fuselage design that characterized most American gliders. Instead, they embraced a flying wing concept, closely studying Bonelli's philosophy and incorporating their own ideas on top of it. A half-size prototype model was created in late 1942 by Bolus Sailplanes, with Bolus and his team considering the initial test results to be good. The first full-size glider prototype, named the MC-1 glider, was produced by General Airborne Transport. Following the closely followed design of the half-size model, initial factory tests once again indicated the potential of the new design. The full MC-1 design was envisioned to be larger than other gliders of its time. It was characterized by a high wing configuration with a wooden frame and fabric covering, all while retaining Bonelli's philosophy. With a wingspan of 110 feet and a length of 67 feet, the MC-1 boasted substantial dimensions. Bolus aimed for a cargo capacity of up to 15,000 pounds, facilitating the transport of both cargo and troops through two large cargo doors located at the glider's front for easy access and rapid deployment during battle situations. The intended operational method involved towing the XCG-16 into the air by a C-47 or C-54 Air Force transport plane, which would then release the glider to continue its flight independently. The glider featured a twin-boom design for the tail. Designed with spoilers, the XCG-16 could deploy them to reduce lift and increase drag, enabling rapid descent and short landings on various terrains. Additionally, the glider was equipped with retractable landing gear, deployable for landings on rough ground. The maiden flight test of the MC-1 began on the 19th of July 1943 at March Field, California. The first test run proved to be a success and was commended by military and business observers. A second test flight was scheduled at March Field on the 11th of September 1943, but this run ended in disaster. Among the crew and passengers aboard the glider were notable aviator and businessman Richard Chichester DuPont and military glider specialist Colonel Ernest Gable, who was set to pilot the MC-1 for its demonstration. During the demonstration, the glider was towed by a Lockheed C-60. Shortly after takeoff, an unintended encounter with the C-60's prop wash caused the glider to violently sway from side to side. Compounding the issue, The weight ballast inside the glider had not been properly secured and began to shift, exacerbating the rapid tilting of the XCG-16. Recognizing that a crash landing was imminent, 3 of the passengers, including DuPont, attempted to parachute from the glider as it continued its descent. While 2 passengers successfully landed safely, DuPont tragically lost his life when his parachute didn't open in time. Colonel Gable remained on the glider and also lost his life when it ultimately crashed into the ground. Despite the tragic setback at March Field, Bolus continued with the design, and the US military awarded a contract to the General Airborne Transport Company in November 1943 after negotiations. The contract approved the construction of 3 MC-1 units. 2 flyable and 1 for static tests were awarded by the USAF. The completed full-sized MC-1 gliders were also given the military designation XCG-16, and the name stuck. Only 1 completed XCG-16 unit was manufactured and submitted for USAC testing. Test pilots and engineers acknowledged the XCG-16's strong aerial performance, highlighting its excellent stability and maneuverability. However, military observers concluded that the glider fell short of expectations in terms of cargo and loading capabilities, deeming it unsuitable for combat situations. Consequently, no additional units were produced. There was initial consideration of repurposing the glider for new Air Force experiments. In 1944, the US military explored the concept of extending the range of existing transport and bomber aircraft by utilizing trailing gliders to carry fuel. The XCG-16 airframe was handed over to the Cornelius Aircraft Company, known for building gliders, to modify and test the forward-swept wing design, capitalizing on the XCG-16's robust capabilities. The Cornelius Company made several alterations to the glider, renaming it the XFG-1 and prepared it for a test flight. However, the first XFG-1 model crashed during a demonstration in October 1944. Although a second model was produced by Cornelius following the Bolus format, by that time the US military had lost interest in the project, leading to the discontinuation of further development. The Ryan XV-5 Vertifan was an experimental jet-powered VSTOL vertical short takeoff and landing aircraft developed in the 1960s. The United States Army commissioned the Ryan VZ-11RY in 1961, later redesignated as the XV-5A in 1962. This initiative was part of the Army's exploration of VSTOL capabilities, alongside the Lockheed VZ-10 Hummingbird, which was later redesignated as the XV-4 in 1962. The XV-5 was equipped with 2 General Electric J85 GE5 turbojets, each providing 2,658 pounds of thrust. Vertical takeoff and landing VTOL capabilities were achieved through the use of General Electric X3535 lift fans integrated into the wings and a smaller fan in the nose. These lift fans were powered by engine exhaust gas. Each wing featured a 62.5-inch diameter lift fan with a hinged cover on the upper wing surface, which could be opened for VTOL operations. The 36-inch nose fan played a role in pitch control but posed challenges in terms of handling characteristics. The lift fans collectively generated vertical lift of approximately 16,000 pounds, which was nearly 3 times the thrust produced by the turbojets. Yaw control was facilitated by a set of louvered vanes beneath each wing fan, enabling the vectoring of thrust fore and aft. The XV-5 Vertifan was a part of the Army's exploration of innovative VSTOL technologies during the 1960s, showcasing unique lift fan configurations for vertical takeoff and landing. The engine power setting determined the lift from the fans, as fan RPM was determined by the exhaust output from the J85 engines and the load on the fan. Roll control was by differential actuation of the wing fan exit louvers. Aircraft performance was subsonic, with delta wings superficially similar to those on the Douglas A4 Skyhawk. The Vertifan had an unusual intake position above the 2-seat side-by-side seating cockpit and a T-tail. The XV-5A was painted in army green, while the XV-5B had a white NASA color scheme. Despite its unique design, the lift fans on the XV-5 didn't generate the anticipated thrust, and the transition between vertical and horizontal flight proved to be challenging and abrupt. This aircraft marked one of the last crewed endeavours by Ryan, a company that shifted its focus to drone manufacturing in the mid-1960s. The XV-5 was part of a diverse array of attempts to create successful vertical takeoff aircraft. However, the lift fan system used in the XV-5 was heavy and occupied a considerable internal volume. Only the Hawker Siddeley Harrier remained operational by the turn of the 21st century, along with technology enabling the use of a shaft-driven fan in the Lockheed Martin F-35B. The combination of the J85 engine and lift fan in the XV-5 was a precursor to developments that led to the first high bypass ratio engine by General Electric, the TF-39. The lift fans were driven by turbine blades mounted around the fan's periphery, with a mass flow 13 times greater than that of the gas generator and resulting in a threefold increase in thrust compared to a propelling nozzle. Following the demonstration that large volumes of air could be moved through a lift fan, an 80-inch tip drive fan, turned through 90 degrees and powered by a more potent J79 engine, was constructed to showcase an efficient cruise fan. This concept of a large diameter cruise fan was incorporated into the General Electric TF-39 engine utilized on the Lockheed CF-5 Galaxy. The XV-5, while not achieving widespread success, played a role in advancing lift fan technology and contributing to subsequent developments in aircraft propulsion. Two 12,500-pound XV-5As were evaluated in late 1966 by 15 test pilots. One was destroyed in a crash during a public flight demonstration on the 27th of April 1965, killing Ryan test pilot Lou Everett. As a result of this accident, the conversion switch was changed to a lift-lock toggle and relocated on the main instrument panel ahead of the collective lever control. The XV-5 presented challenges during landing due to various factors. Yaw control relied on altering the angle of the lift fans in opposing directions, but this method proved insufficient for precise low-speed handling. The duct doors further complicated control, causing significant pitch changes even at low speeds. Additionally, the aircraft experienced poor acceleration during standard runway takeoffs. Promotional materials and tests explored the potential of a rescue version equipped with a winch to hoist individuals into a compartment behind the pilots. However, a tragic incident occurred on October 5, 1966, during trials for the rescue aircraft. The second XV-5 sustained extensive damage when a suspended horse collar survivor sling was drawn into a wing fan. Despite the fan still functioning well enough for controlled flight, Major David H. Tittle, the pilot, suffered fatal injuries due to the ejection seat propelling him out of the aircraft after it hit the concrete airport surface. Following the accident, the second aircraft was reconstructed as the modified XV-5B and testing continued until 1971. An XV-5B is currently on display at the United States Army Aviation Museum in Fort Novosel, Alabama. Despite the cancellation of the program, the ducted fan concept was deemed successful, leading to several proposed follow-up programs. The ducted fans were recognized for their quiet operation, especially for the era, and their ability to operate from standard surface materials without causing damage. This set them apart from other VTOL aircraft, which often require protective mats to prevent ground surface damage from their exhaust, a concern mitigated by the cooler exhaust from ducted fans. In 2004, renowned director Martin Scorsese released the feature film The Aviator, which garnered 5 Oscars. This cinematic masterpiece sparked widespread interest in one of America's most extraordinary figures, billionaire Howard Hughes. Among his many ventures, Hughes undertook the ambitious project of creating a colossal amphibious aircraft known as the Hughes H-4 Hercules. This flying boat, constructed as a singular prototype, made its historic maiden flight on November 2, 1947. Despite only completing a single flight, Hughes's Hercules secured its place in history as the largest flying boat ever built. Its monumental wingspan of 98 meters remains unrivaled to this day, surpassing even the dimensions of aircraft such as the AN-124 Ruslan and the AN-225 Emria. During the early stages of World War II, Allied forces initially underestimated the threat posed by Nazi Germany's submarines. Lessons from World War I had been disregarded, leading to catastrophic losses in naval trade. While losses from German submarine attacks were initially manageable during 1939 to 1940, the situation escalated dramatically in 1941 to 1942. The German Kriegsmarine unleashed a reign of terror across the vast expanses of the Atlantic, sinking nearly 700 Allied ships in the first 7 months of 1942 alone. It wasn't until the latter part of 1942 that the situation in the Atlantic began to improve, primarily due to a significant increase in the number of escort ships deployed to protect convoys. This concerted effort helped mitigate the threat posed by German submarines, albeit after considerable losses had already been incurred. Despite these actions, the threat from German submarines was not eliminated. In such conditions, the idea was born that would protect valuable military goods from Kriegsmarine attacks. Cargo could be shipped across the Atlantic Ocean not only by water, but also by air. However, the implementation of this idea would only be possible with the creation of a transport plane of sufficient carrying capacity. To address the pressing need for a solution, shipbuilder Henry Kaiser proposed the design of a large transport flying boat. Renowned billionaire and aircraft designer Howard Hughes enthusiastically took on the challenge of bringing this concept to fruition, resulting in the creation of a giant aircraft that remains unparalleled to this day. In 1942, the US government contracted Howard Hughes to construct a single prototype aircraft, driven by the vision of a sizable flying vehicle to support naval operations. The result was a multi-ton wooden amphibious aircraft with a remarkable wingspan of almost 100 meters. Initially designated as the NK-1 Hercules, this flying boat boasted impressive dimensions that continue to impress. A fuselage spacious enough to accommodate over 700 soldiers, weaponry, and approximately 60 tons of commercial cargo. To provide the necessary power for this colossal aircraft, 8 engines were installed in its wings. The project's development was guided by a specific goal: to construct an aircraft for cargo and passenger transportation while minimizing the use of strategic raw materials. Consequently, the decision was made to build the aircraft from wood rather than aluminum. The envisioned role for this flying boat was to transport troops and various cargoes from the United States to war-torn Europe along a secure air route, circumventing the threat posed by the German submarine fleet. Working documentation for the new flying boat was developed very quickly, which cannot be said about the pace of the aircraft construction itself. The works that began in 1943 were fully completed only by the middle of 1947. This slowdown in the construction of the aircraft was influenced by several reasons, ranging from the end of the Second World War, as a result the military lost interest in this car, and ending with various legal proceedings against Howard Hughes. Disputes regarding the funding for the project persisted throughout its execution, reflecting differing opinions on its necessity. One dissatisfied US senator famously referred to the future amphibious aircraft as a flying forest warehouse, but it garnered another well-known nickname, the Spruce Goose. A substantial sum from the US state budget, totaling $22 million, a considerable amount for the time, was allocated for the project's implementation. However, this funding proved insufficient, prompting Howard Hughes to personally invest an additional $18 million into the endeavor. The flying boat, subsequently renamed the N-4 after Henry Kaiser's departure from the project, marked the 4th aircraft of Howard Hughes's own construction. On November 2, 1947, the N-4 made its inaugural and final flight, piloted by Hughes himself. The aircraft undertook a brief flight, ascending to an altitude of 21 meters and traversing a 2-kilometer stretch along the coast of Los Angeles. With this flight, the saga of the Hercules nearly came to a close, transitioning abruptly from the realm of active aviation to that of a museum exhibit. Ultimately, this costly and sizable flying boat proved to be of little practical use at the time. The Hughes H-4 Hercules was characterized by a hull, a cantilever wing, and 8 radial engines. The flying boat had a vertical and tail plumage, as well as fixed wing floats. The entire structure of the aircraft consisted of laminated wood, but contrary to the nickname in the construction of the flying boat, it wasn't spruce, it was birch. At the Howard Hughes plant, woodworking was able to achieve high aviation standards. The construction of the aircraft involved creating full-size patterns of structural elements, from which matrices were produced for molding the parts. The thinnest piece, with a thickness of 1.2 mm, consisted of 3 layers, each 0.4 mm thick. Conversely, the thickest part measured 254 mm in thickness and comprised 200 layers of veneer, each 1.27 mm thick. To maintain the integrity of the veneer layers during gluing, double-capped nails were utilized. Once the glue had set, these nails were removed using a special nail puller, resulting in the extraction of approximately 8,000 nails across the entire flying boat. The resulting holes were then sealed with a specialized putty. Following assembly, a thin layer of primer was applied to the surface, succeeded by a layer of rice paper and 2 coats of protective lacquer. The exterior surfaces of the aircraft were coated with aluminum paint, concealing the fact that the aircraft's underlying structure was composed of ordinary wood. Both the aircraft's skin and its structural components appeared as if they were made of aluminum. The cargo compartment of the amphibious aircraft featured 2 levels, interconnected by a spiral staircase. Hinged doors located at the nose of the aircraft facilitated the easy passage of 2 railway cars or a Sherman M4 tank. This design ensured the versatility and practicality of the aircraft for transporting various types of cargo. At that time, the Hughes H-4 Hercules was the only aircraft that was able to transport the tank through the air. In the best traditions of submarines and ships, 18 seal compartments were provided in the design of the seaplane. 6 of them were enough to keep it afloat. The electrical equipment of the aircraft operated from direct current with voltage 120B, since with traditional 24B, the cross-section of the wires, the length of which reached 50 kilometers, was very large. The seaplane was to be lifted into the air by 8 huge radial air-cooled R4360 Wasp major piston engines from Pratt & Whitney. Each of these engines developed 3,000 horsepower. The engines of the aircraft were equipped with 5-meter 4-blade propellers. Of the 4 engines positioned closest to the fuselage, 4 were capable of generating reverse thrust, granting the giant aircraft the remarkable ability to maneuver independently in reverse and execute tight turns. The expansive size of the flying boat facilitated in-flight engine repairs, as special passages within the enormous wing allowed access to the engines. At the point of attachment to the fuselage, the wing section reached a height of 4 meters. Despite its unprecedented scale, only a crew of 3 individuals was required to operate the aircraft. The collaborative effort between Hughes and Kaiser aimed to produce the largest aircraft ever constructed, surpassing any previous aircraft in size by a staggering 7-fold. This ambitious project stands as one of the most remarkable endeavors in aviation history. The determination and valor of Howard Hughes and his dedicated team, who persevered despite numerous challenges, culminated in the historic flight of the H-4 Hercules. However, tensions arose within the project leadership, leading to significant contradictions. Henry Kaiser advocated for the construction of a 70-ton aircraft to adhere to deadlines and present a finished product to the military. Conversely, Howard Hughes insisted on building a 200-ton airplane, necessitating greater investment of time and resources. This discord ultimately led to Kaiser's departure from the project, while Hughes became increasingly enamored with the idea, incorporating new improvements and proposals that further prolonged the construction timeline of the flying boat. As a result, in 1942, this order was urgent for the US government, but by 1944 it lost its relevance. By this time, the situation on the fronts of World War II had changed radically, and the interest of the United States in the project gradually faded away. The US government had contemplated cancelling the contract for the seaplane's construction, but by then, Hughes's motivation had transcended mere practicality. He had become consumed by the idea of creating a cargo aircraft that would surpass even the most extravagant imaginations of his contemporaries. On November 2, 1947, the Hercules was launched, and Hughes, alongside his small crew, initiated the aircraft engines for the first time. Following several water taxi tests in front of a sizable audience, predominantly journalists, the flying boat lifted off from the surface of the Los Angeles harbor without any prior announcement, embarking on its inaugural and final flight. Maintaining an altitude not exceeding 20 meters, the Spruce Goose traversed approximately 2 kilometers at a speed of 120 kilometers an hour before executing a flawless landing. This unauthorized test flight, undertaken in defiance of an official ban on taking the plane airborne, served to silence numerous critics of the project, demonstrating that the largest aircraft in history was indeed capable of flight. Many regard this flight as one of the most significant moments in the annals of aviation history. Following its historic flight, the Spruce Goose returned indefinitely to its hangar, a colossal structure specially constructed to house it and prevent it from ever taking flight again. At Howard Hughes's behest, until his passing in 1976, the flying boat remained in a state of perpetual readiness, with its engines started every month. Initially, a team of 300 individuals monitored the aircraft's condition until the 1950s, when the staff was reduced to 50 people. Nevertheless, the annual cost of maintaining the Air Giant in flight-ready condition amounted to approximately $1 million. Additionally, the construction of the hangar where the Hughes H-4 Hercules was preserved for eternity incurred costs of around $2 million. Currently, this unusual aircraft is an exhibit at the Aviation Museum in McMinnville, Oregon, where it was transported in 1993. At the same time, over the past 50 years, this flying boat has become one of the most beloved artifacts of the United States, moving from a state of almost total uselessness to the category of object of cultural heritage. Today, the story of the Hughes H-4 Hercules, which soared into the sky only once in its lifetime, is revered as a testament to its creator's unparalleled resolve to see the project through to completion, transforming the aircraft into an emblem of the 20th century. Regarded as a symbol of determination and ingenuity, the Spruce Goose continues to captivate the imaginations of people worldwide. Drawing over 300,000 visitors annually, the aircraft stands as a living testament to Howard Hughes's extraordinary vision and perseverance. Its towering presence serves as a reminder of the boundless ambition and unwavering commitment that characterized an era of pioneering aviation endeavors. Through its enduring legacy, the Hughes H-4 Hercules remains an enduring symbol of human achievement and innovation. Built for the Air Force by Martin, the X-24A was a bulbous-shaped aircraft with 3 vertical fins at the rear for directional control. The X-24A boasted a weight of 6,270 pounds without propellants, with dimensions measuring just over 24 feet in length and nearly 14 feet in width. On April 17, 1969, Air Force Major Gerald Gentry piloted the X-24A for its inaugural unpowered glide flight. Gentry also commanded the vehicle during its first powered flight on March 19, 1970. Over the course of its operational lifespan, the X-24A undertook 28 flights, contributing to the validation of the concept that a wingless vehicle could execute unpowered landings akin to the HL-10 program. Decades later, in a cost-saving measure, the X-38 program managers opted to utilize the X-24A design, leveraging its complete aerodynamic database to minimize the need for additional wind tunnel tests that would have been necessary for a completely new design. The X-24A recorded its fastest speed of 1,036 miles per hour, Mach 1.6, with its highest altitude reaching 71,400 feet. Both of these milestones were achieved by NASA research pilot John Mach, who also piloted the craft on its final flight on June 4, 1971. The X-24B's design evolved from a family of potential re-entry shapes proposed by the Air Force Flight Dynamics Laboratory, each with higher lift-to-drag ratios. To reduce the construction costs of a research vehicle, the Air Force opted to return the X-24A to Martin for modifications. These alterations transformed its bulbous shape into a configuration resembling a flying flatiron, featuring a rounded top, flat bottom, and a double delta planform culminating in a pointed nose. John Mank took the helm for the maiden flight of the modified X-24B, piloting its first glide flight on August 1, 1973. He also commanded the vehicle during its inaugural powered mission on November 15, 1973. Notably, among the X-24B's final flights were 2 meticulously executed landings on the main concrete runway at Edwards, showcasing the operational feasibility of precise unpowered re-entry vehicle landings. These pivotal missions, executed by Mank and Air Force Major Mike Love, played a crucial role in shaping the flight procedures for modern space shuttle landings. The X-24B's last powered flight was on September 23, 1975, with Bill Danner at the controls, marking the conclusion of rocket-powered lifting body flights at the Flight Research Center. Interestingly, Danner also piloted the final X-15 rocket plane mission approximately 7 years prior. The X-24B achieved a top speed of 1,164 miles per hour, Mach 1.75, during a flight piloted by Love on October 25, 1974. Its highest altitude reached was 74,100 feet, accomplished by Mank on May 22, 1975. Today, the X-24B stands proudly on public display at the Air Force Museum located at Wright-Patterson Air Force Base in Ohio, serving as a tangible testament to its significant contributions to aerospace research and development.
From 1933 until the end of the Second World War, German aviation led the world in aerodynamic design and technical innovation. Long before the outbreak of hostilities, German industry produced an armada of technically superior warplanes. When war broke out, the Luftwaffe quickly overwhelmed some of Europe's most vaunted air forces. Classic designs like the Bf-109 fighter and Ju-88 proved to be superior fighting machines, while others like the Blumenvoss Bv-141 became one of aviation's true oddities. The Blumenvoss company was one of the first to respond with their Bv-141. Designed around the concept of maximum all-round view, the Bv-141 was in many ways a problem looking for a solution. The unorthodox design featured an asymmetric layout with the radial engine installed at the front end of a port-side tail boom and an extensively glazed crew nacelle mounted to starboard. Unusual and radical in design, the Bv-141 performed surprisingly well, but in the end it was considered too unconventional and it was cancelled in 1943.
Yes, in my meanderings throughout Germany, just after the capitulation, I was looking for unusual or advanced technology aircraft. And the 141 intrigued me a little, but I had heard that they were at an airfield called Größenhain, which was quite near Meissen. There was a big reconnaissance unit which had many reconnaissance types of aircraft, and I thought maybe the 141 will appear there. So I flew there, and there was no sign of one, but I asked if I could speak to some of the POWs who were in the cage there, and one of the chaps told me that a 141 had indeed been there, but the last he remembered of it was not too long ago. It had had an engine problem while flying nearby and had landed on an emergency strip east of Größenhain. So I flew over in that direction looking for this strip. but it wasn't really a strip, I found. It was a small airfield. And it was, by this time I'd moved into the Russian occupation zone. And I decided to land there because I had already found that that stage after the war, the Russians were still very amenable to the Brits because we had come in at the early stages of the war to help them. Anyway, when I landed, there weren't a lot of aircraft there, and there was a Russian commissar and with an interpreter, and I asked if there was a 141 there. He didn't really know things like the aircraft numbers, but he said there were 1 or 2 aircraft left, but his people had examined the airfield, taken away what they wanted, and the rest was left for destruction. So I said, could I have a look around, see what it was? He said, well, yes, why not? Because it's all going to be destroyed anyway. And in one hangar, there was indeed a 141. It had regularly had its engines run up by Feldwebel, who was available. And I said to him, was the aircraft flyable? And he declared, oh, yes, it was. I rather suspected his motive, so I wasn't too sure of what he was saying or believing what he was saying, because I think he had hoped I would fly him out of there and out of the Russian zone. But the Russians were obviously not going to play with that. Anyway, I thought I'll take his word for it and have a go at this. And the commissar didn't object. He said, as long as I stayed within sight of the airfield and I'd only have enough fuel to do that, he didn't mind, because it was due for destruction anyway. And so he let me fly that, and I had about 30 to 40 minutes in it to try out this theory that it flew very nicely in a straight line when on an angle of bank of 90 degrees. And after about 2 or 3 goes at this at various speeds and heights, I had trouble with the engine. So I had to return to base. And so I formed an impression that it probably did what it said it could do. But its real reason for failing, in my opinion, was it certainly wasn't an aircraft in the same category of handling as the Focke-Wulf 189, which I had already flown and was its competitor.
Another odd-looking aircraft was the Focke-Wulf 189. The completely glazed central nacelle, twin engines and tail booms were considered too radical for conservative Luftwaffe officials. Performance, however, won the day. Known as the Flying Eye, the FW-189 proved supremely versatile, universally popular, and one of the most reliable aircraft ever to see Luftwaffe service. During combat operations, the FW-189 surpassed all expectations. Despite flying low over the battlefield and taking large amounts of damage, it had the ability to absorb punishment and fight another day.
So I think that killed it more than the theory that it gave the gunner a wonderful field of fire by having no starboard half of the tailplane and being asymmetrically offset to give a clear field of fire to the gunner. So that was my experience of it. Not very impressive, but interesting.
In the early part of 1953, a new concept in military aircraft was about to take shape, a concept which evolved from the joint effort of Air Force planners and Lockheed designers, shaped by Air Force experience in recent conflicts. The concept of the lightweight fighter, supersonic, low in cost, easily producible, the XF-104. Work began in March. Plans had to be drawn up, a mock-up completed, tooling prepared, and plant space cleared so that production crews could start work on the first of 2 prototypes. A challenging schedule was set up. The first prototype was to be completed and into flight test by March of 1954, less than a year away. Work went ahead swiftly. Experimental jigs were designed and put together in the shop area. In adjacent areas, machined parts were made, parts which had to be milled and bored and cut, shaped for use in early fabrication stages. Actual fabrication was soon underway, and through the production processes of sub-assembly and assembly, the F-104 began to take shape. In the meantime, wind tunnel tests were conducted in the company's subsonic tunnel. A range of low-altitude, low-speed conditions were generated to simulate the force and load factors which would act on the F-104 during takeoff and landing. Measurement of these forces and loads, in turn, would furnish information to the design of landing gear, flaps, and controls. Wind tunnel work at this time also included a series of flutter tests conducted through a wide range of airspeed-altitude combinations. A direct control device was used to bend the wings to a calculated degree. Motion pictures furnished a visual record of results, while direct readings of flutter amplitudes and frequencies were made by oscilloscope. Sudden release of the wing induced flutter. Engineers used the wind tunnel to further advantage in a series of tip tank tests. High-speed photography showed that separation of the tank from the wing was immediate and clean. By mid-October, the main fuselage was well underway, and work went ahead on the empennage, wing, and stabilizer. In the meanwhile, Lockheed engineers had gone to the Ames laboratory at Moffett Field, where the superb technique and equipment of this NACA facility were used to prove out design of the 104 and to gather data on its aerodynamic behavior in both subsonic and supersonic ranges. Tests aimed at determining the span-wise distribution of various force and bending moments. Leading and trailing edge structures were investigated, as well as the effects of tail buffeting. The final series of wind tunnel tests was carried out at the NACA facility at Langley Field, adding a full range of transonic data to the subsonic and supersonic data already collected. Free flight tests provided further and highly realistic confirmation of design ideas. 5-inch high-var rockets were used to impel a scale replica of the F-104 straight-thin wing through the air at supersonic speeds. A gun sight camera mounted on the rocket photographed wing behavior during flight, making available a record for later study. A replica of the 104 tail section was tested in the same way. Towards the close of 1953, construction was well along on the forward section of the fuselage. It was taken from its jig on December 1st and moved to the assembly area for mating with the aft fuselage section. Immediately before mating, each section was weighed to determine that actual weight did not exceed planned weight. In the meantime, the wings had been finished so that they could be joined to the fuselage as soon as it was ready. While the manhandling method shown here would not be used in production phases, it does serve to show the simple design and lightweight qualities inherent in the 104. With the fuselage almost ready for outfitting, attention was given to the items which would be installed in it. An exhaustive series of tests, for example, was going forward at the drop tower, where the 104 landing gear was mounted on the testing apparatus and subjected to shocks and loads far in excess of any it would experience in actual use. After drop tower tests had proved structural strength, the gear was installed in the 104 prototype. A series of run-throughs checked clearances, hydraulic activation, and other operational features. Further valuable time was gained on 104 development by handling several projects concurrently. Armament is an example of this kind of parallel growth. Specialists devised and tested in mock-up a storage box to hold 750 rounds of 20mm ammunition and provide a direct free-flow feed to the T-171E2 gun. With revolving barrels and a very high adjustable rate of fire, the T-171E2 has been chosen as the most satisfactory weapon for the prime mission of the XF-104, that of day or night, air-to-air fighter. The choice is by no means rigid, however. The 104 promises considerable versatility, and provisions have already been made for the installation of a rocket platform in the present gun bay. The platform will be extended for firing and retracted after use. Meanwhile, the first 2 months of 1954 saw the first 104 prototype drawing close to completion. With the mating of the aft fuselage section to the main section, major assembly was complete, and the way stood open for the running of vibration tests. These tests determined the natural frequency patterns for the entire 104 structure. When the vibration test program was complete, the 104 was ready to enter flight test. The F-104 left the plant in the early morning of February 25th. Strict security prevailed, and by daylight the prototype arrived at Edwards Air Force Base, 347 days from the go-ahead date. Flight crews began at once a schedule of pre-flight work, submitting systems and operating parts to a thorough round of checks and rechecks. The engine selected for early flight testing was the Wright J-65W1. Thrust of the J-65 is sufficient to guarantee supersonic performance for the 104. The airplane can accommodate any of several alternate power plants, and with such an engine as the General Electric J-79, for example, speed and performance would be superlative. Engine run-up was a necessary prelude to flight test, now only a few days off. A major flight safety feature of the 104 is that seat ejection is downward. Getaway is clean and immediate, with no possibility of canopy interference or of the seat striking portions of the craft during ejection. Downward ejection also enhanced the simplicity of cockpit layout and canopy and controls design. In the matter of flight station arrangement, Lockheed engineers spent many hours in consultation with Air Force pilots. The pilots made clear their recommendations for a practical, efficient cockpit, and the F-104 follows their indications. Controls are logically grouped and easily operated. In the 104, primary controls are the conventional stick and pedal type. The final pre-flight procedure consisted of a controls check. A cable system operates the rudder. Stabilizer and ailerons are controlled by hydraulically operated, irreversible systems. Secondary flight controls include leading edge flaps, landing flaps, and dive flaps, all power operated. Just before the date of the first flight, a series of taxi runs was made. On February 28th, 1 day ahead of schedule, the craft became airborne. On the morning of March 5, 1954, 355 days from contract signature, the 104 was ready for its second flight. This flyover offers a good comparison of the size and plan form of the 104 with other military types. The thin, straight wing, with its 10 degrees negative dihedral, conferred excellent lateral stability and side-slip characteristics on the craft. Control response was quick and sure. The airplane came through. It handled firmly, surely.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.